Welcome to this year's final of the Iypt. It's a great privilege for me to be chairing this fight. We have here the 4 best teams, but before we start, I would like to thank all of you for coming, for participating, for the hard work you have done over the past months. A lot of effort has gone in to preparing for the problems. Also, your teachers have worked tirelessly, I'm sure, to get you here today. And it's an achievement for all of you to go to Iypt, and I think it's something you can all be very proud of yourselves. So a big round of applause to all teams. The best 4 teams after the preliminary rounds are here today with us in the final. And I would like to start this fight with briefly, everyone here? Okay, I would like to briefly start with an introduction round so that we all get to know yourselves. Can we start with the reporting team from China?
Hello everyone, this is Team China here. My name is Zichuan Peng. I'm the captain of Team China. This is Jingsong Zhang, Weiran Niu, Jiaying Zhang, and Zhiyao Chen. And that's all of us. Thank you.
Thank you.
We're going to be presenting problem number 8, levitating fluid, for this round.
Levitating fluid, yes. Then
So hello everyone, this is Rochil, Benjamin, Alan, and I'm Benedict. Unfortunately, Maxim is missing because he has to left early for his graduation, but we still be doing this. And we will then be presenting problem number 6, the dripping faucet. And of course, I have to introduce our mascot, Horst. So we are looking forward for a pleasant physics fight. Thank you.
Thank you.
Hello everyone, we are Team Slovakia. My name is Lubomir, and with me in the team are Natalia, Anna, Luisa, and Jakub. And we also have our mascot, Laura. We will be presenting problem number 5. Really looking for a good fight and wish everyone good luck. Thank you.
Good morning, everyone. We're Team Singapore. I'm Austin, the team captain, and this is Kabilan, Jonathan, Lucas, and Duan Yu. And this is our mascot, Mark the Monkey. Today we'll be presenting problem 9, magnetic assist, and we hope to have a pleasant physics fight today. Thank you.
Thank you. So now, having introduced all the teams, I would like also to give a chance to our jurors to give a brief introduction, maybe starting over there with Michael.
Good morning, everyone. My name is Michael Zellinger. I'm a physics and math teacher in Austria, and I study computational sciences, physics and math. And I wish you all the best for this interesting physics finals. And yeah, and it's the 3rd time as a juror at an Iypt, and the 1st time in the final for me, so I'm very curious how it works.
Good morning, everyone. My name is Kerry Parker. I'm a physics teacher in New Plymouth in New Zealand. It's a real great pleasure to be here and a privilege and an honor to be selected to be the juror. I have to confess to being pretty awed by what I've seen from some of you so far, and I hope I can follow all the hard maths. Good, have a great fight and enjoy.
Hello everyone, I'm Georgi Khomeriki from Georgia. I work in cosmology in Kansas State University. Good luck to you all. Thank you.
Good morning, everybody. My name is Daniel Keller. I'm from Switzerland. I have studied physics at ETH years ago, and since then I have taught physics all the time. I've been involved in the SYPT and Iypt since 2005, and I'm looking very forward to the great final fight here, and I'm very happy to be a juror. I wish you all good luck and enjoy.
Thank you.
Good morning, my name is Vitaya from Thailand. I teach university physics and been involved with the Iypt since 2016, so nice to meet you.
Hello, my name is Andreas Isaksson. I'm one of the local jurors from Sweden. I'm from Chalmers University of Technology, and that's a bit up north to here. And I also look forward to seeing what you have to present to us.
Good morning, everyone. I'm Mihai Hömösrei from Hungary, physics teacher in Budapest, involved in Iypt since 2013, and I'm pretty glad to be here and see your nice works. Thank you.
Thank you.
Good morning. Good morning. My name is Tomasz Gryczuło. I'm working at University of Wrocław, and I also used to be a physics teacher in all the levels of Polish school. I'm so glad to be here with all of you, and I wish you a successful fight.
Good morning, everyone. My name is Xiaoyang Chen. I am the team leader juror from Canada, and I currently study experimental condensed matter physics at the University of Toronto. And I wish everyone have a wonderful fight today, and good luck to all the teams.
Thank you.
Good morning, I'm Claire Byun, a team leader from Korea and also a professor at the Gyeongbuk National University teaching physics and engineering. And I'm very honored and also excited to see the best of this year's Iypt, and good luck to you all and have fun. Thank you.
Thank you. And just very briefly, I'm Eric Schettenleib. I'm a former participant of Iypt. I studied physics, but now switched to the dark side and work in the financial sector. All right, I think just one small remark on the logistics. We have the privilege of having a fight of 4, which means we will be here for the next 5.5 hours. And I know it's long, I know you might be all tired, but also during the preparation phase of the opponent and the reviewer, or also during the grading of the juries, it's important that they can concentrate. So I would ask you to remain as quiet as possible so that the teams and the jurors can concentrate as well. All right, with that said, and if there are no technical issues, I think we are ready to start. So can we have 1 minute for the reporter from China? All right.
Hello, everyone. I'm Jingsong Zhang from Team China, and I'm reporting problem number 8, levitating fluid. Now, here, let's review the problem. Here, when a container partially filled with liquid is oscillated vertically and air is injected at the bottom of the container, the fluid can levitate. Investigate the phenomenon. So here we think the term oscillate means that a sinusoidal vibration with a fixed amplitude, and the term levitate means that the upper liquid stays above a gas layer and not connected to the liquid below. Now here we listed some influence factors, which includes the liquid parameters, so the oscillation properties, and also the container parameters. The presentation is split up into 4 parts, and let's first come to the series of experiments. Now here you can see our experimental setup with the shaker connected to a signal generator and an amplifier. Now first we modify the acceleration amplitude, and you can see under small acceleration we can see that the levitation is unstable or it cannot happen at all. And under medium acceleration we can see a more stable levitation. And under even larger acceleration, we can observe the large disturbances on the interfaces. And we can find there's 2 thresholds separating these phenomena, which we'll focus on in our investigation. And here you can see a video of multiple injections. We can find that every time the air is injected, the liquid layer falls down a little bit and gets stable again, which means there are some correlation between the liquid layer and the gas layer. And for the size of the container, here we can see that a small container is easier to levitate the liquid, and a large container makes it harder to levitate. Now, for the viscosity of the liquid, here we can see that a less viscous liquid, such as water, is very hard to levitate, but a more viscous liquid like glycerol is easier to levitate, and it also has more stable interfaces. Now, these are the preliminary results. First, there are two thresholds, the stability of lower interface and the large disturbances on the interfaces. And also, the small containers and larger viscosity are easier for liquid levitation. Now, let's come to the theoretical analysis. There are three parts of our theory: the oscillation transmission and mechanism, the lower phase stability, and the Faraday waves on the liquid surfaces, as we observed. Now, here we start with the vibration transmission. So we already know that the liquid needs vibration to stay levitated, and with some estimation, we can know that the vibration is mainly transmitted by the gas layer in between. Now, from this, we can give an equivalent model considering the mass as the liquid layer as a whole mass block, and the gas layer in between as a spring. Then the system is equivalent to a damped oscillator model. Now, after setting a series of variables as shown in the figure, we can give a typical damped forced oscillation equation, in which the omega resonant is the eigenfrequency, and the gamma is a non-dimensional damping coefficient whose value will be determined in the experiments. Now, by solving the equation, the amplitude ratio and the phase difference between the fluid and the container can be given. Now, as you can see from the schematics, we can see the characteristics of a resonance curve, and that means that the eigenfrequency has to match the oscillation frequency in order to transmit the vibration effectively, and this explains the correlation between the liquid and gas layers observed in the pre-experiments. Now we move on to the quantitative analysis of the thresholds. Note that here we're no longer studying the liquid layer as a whole, but we're focusing on the evolution of the disturbances on the liquid layer surface. Yeah. And first, for the lower interface stability, according to the literature, the main reason for the instability is the Rayleigh-Taylor instability, which means that for a two-fluid horizontal interface, if the density of the upper liquid is bigger than the liquid below, then the gravity would enlarge any disturbances and leading to instability. Now, for this canonical disturbance mode, we can use the Bernoulli's equation to derive the kinetic equation of this disturbance mode, in which the omega 0 is the dispersion relation. And considering the viscosity of the liquid, we here add a viscosity term beta, which is positively correlated to the viscosity mu, and get the final equation as shown here. Now, for the dispersion relation mentioned, we can use the standard gravity capillary dispersion relation and take the infinite depth situation, because the liquid layer in our situation is thick enough. Now, for the lower interface, the gravity term can be seen as inverted, because the relative position of the air and the liquid is inverted compared to normal cases. So we just need to add a negative sign for the gravity term. And you can find that when k is relatively small, the omega square can be negative, and which is the source of instability. Now, however, as the container walls exist, some modes with too small a k are invalid. For example, for the square containers, we can give this k minimum equals pi over L from the standing wave conditions. Now, the interface would be stable if we can stabilize all modes with k larger than k minimum. So under the oscillation, a Kapitza's method can be used to correct the dispersion relation by adding an oscillation term, which represents the average effect on the dispersion relation by the oscillation. And from the kinetic equation, we can solve the exponential growth rate of disturbances, and from which we can find that the stability of interface only requires on the corrected dispersion relation, which means it only requires the acceleration amplitude. And quantitatively from this, we can give this critical acceleration, and we can find that it is just linear to the oscillation frequency. Of course, using our theories, we can also explain the influence of other parameters. For example, the threshold is related to the size, to the half power, and a larger viscosity means a smaller growth rate, which can help the gas layer to form. And for the same reason, a faster injection can help to reach the stable range before the instability breaks off the whole injection process. And the last part of our theory is on the excitation of Faraday waves on the surfaces. In the right, you can see Faraday waves on the upper surface. And this excitation can be explained by the parametric resonance theory that if the oscillation frequency is 2 times the eigenfrequency of some wave mode, then that mode would be excited. Note that here we no longer apply the Kapitza's method because the conditions are no longer met. Now, considering damping, the critical acceleration for amplification is given here according to literature. And in this limit of small viscosity or high frequency, the form of viscosity term beta can be determined as shown here, and from which we can then derive the critical acceleration. Now we can see that the critical acceleration is positively correlated to frequency and viscosity. However, the small viscosity limit is not necessarily valid to the actual liquid. So our theory might need some quantitative correction. Now first, as you can see, we non-dimensionalize the viscosity term beta as shown here, and then we add a power index n on the whole expression, which gives us a new formula of critical acceleration. Now the undetermined index n coefficient can be obtained by fitting the experimental data. Now let's move on to the results of our experiments. So here's the experimental setup with a 2,000 flicks per second camera capturing the motion of the liquid and the container. And here's the signal generator, the injector, and the illumination. Now the liquids used in this experiment are glycerol and diluted honey, which have different viscosity coefficients. Now the container is a 5 × 5 × 20 centimeters rectangular container. And for the data processing, we use a shape detection algorithm of MATLAB to determine the center rate of the liquid layer. Now we'll verify our theories one by one. First, the oscillation transmission. A set of experiments changing the oscillation frequency was conducted during a single levitation in order to control the variables. And because the parameters depend on the height of the liquid layer and the gas layer, so we should keep them unchanged. Now, the corresponding amplitude ratios and the phase differences can be determined using these captured curves of motion. Now, by fitting the experimental data, we can get the eigenfrequency and damping coefficient for this set of experiments shown here. And you can see that the fitting is quite good, and the results from the amplitude and the phase are close to each other, which proves the correctness of our oscillation transmission theory. Now, the second part is of the quantitative measurement on the Rayleigh-Taylor instability threshold. Now, the experimental data points are consistent with our theoretically derived linear relationship. And the last part is on the Faraday waves excitation. And you can see from the graph that the quantitative agreement is not so good, which means the theory correction is indeed necessary. Now, if we fit the data with the corrected formula, we can get the index n equals 0.473, which is very close to 0.5, and on which we can give an explanation of it using the dimensional analysis. And you can see now the theory fits the experiment pretty well, but of course, simply fitting the theoretical curve is not persuasive enough. Therefore, we do the experiment with another type of liquid, and we use the same numbers we just obtained, as you can see here. We can see the theory still agrees pretty well with the experiments, which proves the generality of our theory correction. And here are the error analysis of our investigation. So theoretically, we neglected the effect of liquid on the container wall and density and air density, and their influence are smaller than 1%. And experimentally, we think that the liquid properties may change due to the injected air. And for this, we measure the viscosity with viscometer after the experiment. Now, finally, we'll give a conclusion to our work. Now, first, we developed an equivalent damped oscillator model of oscillation transmission, and we proved it reasonable by experiment. We also developed quantitative theories for the two thresholds observed. Now, for the Rayleigh-Taylor instability, we derived that the critical acceleration is linear to the oscillation frequency. And for the Faraday waves excitation, we found that the critical acceleration is positively correlated to both frequency and viscosity. And the acceleration between the two thresholds can lead to a most stable levitation. Now, for the Faraday wave threshold, we also used the index n and coefficient a to correct our theory formulas and proves its generality with different kinds of liquids. Also, for the influence of other parameters such as container size, viscosity, and injection speed, some semi-quantitative results are given, and all the experimental observations are explained. Now, the results can be drawn in a graph as shown, and we'll finally make a brief summary on this problem. So the oscillation is transmitted to the liquid layer by the injected gas layer, and with enough amplitude, the averaging effect of the oscillation stabilizes the lower interface. Under even larger amplitude, the Faraday waves are excited and making the surfaces less stable. Thank you very much.
Thank you. Questions from the opponent.
Okay. First of all, thank you very much for this nice report, but there's still some questions need to be asked. You stated that the shape is an important parameter. Did you vary it in your report?
Yes, theoretically we did.
Experimentally, did you vary
so
the shape of the
experimentally, due to
container?
experimental conditions, we did not, but we give some theoretical analysis.
Also, you stated some estimations for the stable oscillations. Can you state those estimations you made
Yes, I can
here?
show it in this.
Guys, more questions.
Sorry, the estimation of oscillation
Yeah,
transmission.
it's okay if qualitatively.
Yes,
what are the estimations?
The total force is far larger than the viscous force by the
thank you.
walls.
How did you ensure that there was always the same air injected and always at the same place?
As I've said, we have done the experiment.
Did you ensure it or not? Please?
Yes.
Okay. Also, then therefore, did you see any limit in the injected air volume in order to the fluid to levitate or not?
Actually, there are some certain limits. For example, if it's too few, they will just float up, as you can imagine.
So you would have a lower limit and an upper limit.
For the upper limit, yes, because if you inject too much.
Okay, thank you. For your Faraday instability, did you by any chance assume a vorticity flow, free flow?
I'm sorry.
And vorticity free flow. Did you assume this for your theoretical derivation?
The vorticity.
Yes or no?
Actually, I.
Okay, then if this is not answered, we will discuss this later on in the discussion.
Okay.
Also, did you by any chance see an effect on the speed of the increasing acceleration when you increase it faster or slower? Yes or no?
Increasing acceleration? No, we fixed
okay, so we'll discuss this later on.
Thank you. You have time to prepare. flip. Okay, please start.
So, hello everyone, and welcome to Team Germany's report on this year's 8 task problem number, the levitating fluid. As we are all familiar with the task, we start what we would like to see here in this report. So we would like to see in qualitative explanation why the air layer is actually forming and how does it in first order come to this levitation of the fluid, and then why does it stabilize and when it could break up. Then we would like to have seen a controllable oscillation setup with a reproducible air injection, which in our point of view is actually quite hard to ensure this. Also for the parameter variation, we would like to see various viscous liquids being varied, and also the shaking frequency and amplitude, as well as the size and shape of the container being varied and investigated, therefore for both the limits. Also on the theoretical modeling, we would like to have seen here an investigation for the free surface dynamics of the liquid, and also on the stable oscillation part, how is it oscillating and when is it oscillating, and describing it theoretically. Now, coming to our experiments, we really liked here in this the visualization of the sufficient experimental setup used in shaker and a function generator, and also optimized video tracking, and also did vary some of the most important parameter, being the viscosity, frequency, and of course the amplitude of the acceleration. But however, here we were a bit unclear about how reproducible this air injection here is, and we will talk about this then later on in the discussion. Further on, what we were a bit missing was that there was no quantitative investigation of the container size and shape, which on the effects of surface tension have a very crucial part on actually the stabilization of this levitating liquid. Also, the speed of the injected air was here not investigated. Further on, the systematic investigation of the resonance behavior, dependent on the parameters, was a bit lacking, and maybe we can discuss about this later on. And also the quantity of the data and the proof of the given equation with the corrections you have done. We would love to see here a bit more quantity of data actually proving those correlations he showed. Now, for the theory, we really liked this damped spring analogy to the oscillator, which then actually models the stable oscillations we have during the levitation, and also the Rayleigh-Taylor and Faraday instabilities were investigated and identified, and the analogy to the Kapitza effect, Kapitz's pendulum, we really liked. But however, as we already stated in our clarifying questions, there were some estimations made for the stable oscillations where we were a bit unclear, and also there was no explanation on how this air layer in first order actually forms, which then leads to the levitation of the fluid. Also, there was some physically unjustified correction factor which used in his model, which we're going to talk about in the discussion, and also on the question about the vorticity free flow. We will have to discuss this later on, since this was also not clarified in the clarifying questions. And now for our overall impression, the explanation on why the air layer actually formed was not given, so therefore we're going to start with this in our opposition now. For the setup, we generally really liked it, but we are also not sure about the actual reproducibility of the air injection. And for the parameter variation, it was the most relevant, were investigated, but still some a bit missing. And for the theoretical modeling, generally there was a good job done, and we say the task was partially fulfilled. Thank you very much. Now I invite you to the stage.
Okay, thank you for the evaluations and comments. And first, I would like to answer. I would like to clarify some of your questions. Now, first, for the controlling of the injected volume of the air, as we see here, to control, as I said, to control the parameters, we've done all the experiments in a single process of levitation, which means when we inject the air, we keep the liquid layer on the top not to fall down, and then we change the oscillation frequency, and we can get multiple experiment data.
I see this, but when you vary the parameters, how could you then ensure, if you said there was only one single trial for your measurements, how could you with only one experiment ensure that this is actually reproducible? Because what I already asked you about some limits on the lower and upper limit for the volume injected. So I think therefore it is really crucial in order to actually have a reproducible air injection, since the task especially tells us to inject it at the bottom.
I understand you, but as I said, all these experimental data are collected during one time of levitation. So the liquid layer is the exactly same liquid layer, and the gas layer is the exactly same gas layer. The liquid layer never falls down, so that's how we control all the parameters same.
Okay. Then so then I can ask you again, because I'm really not sure about this. How could you investigate the critical
You mean the liquid limit of volume?
You showed us measurements where you compared the Rayleigh-Taylor instability and the Faraday instability to your measurements, right?
Yeah, but as I said,
how did you investigate the Rayleigh-Taylor instability when the liquid didn't fall down? When did you determine to be broken up?
No, I'm sorry. I thought you were asking about this part of the verification, which means the oscillation transmission verification. And for the other parts, for the Rayleigh-Taylor instability and the Faraday instability, of course you need to, for example, change the like, for example, you have to inject it multiple times. But as I said, this time we're not investigating the motion of the whole liquid layer. We're investigating the evolution of disturbances on the surface of liquid layer. So
I agree with you here, but again, my question was, how could you ensure that the air injection from various measurements was always constant? Did you, for example, use a syringe to control the volume? And how did you ensure the position of the injected air volume?
For this,
because I think this is really crucial for the levitation itself.
For this part of the theory, actually, from the theory, you can know that the control of the liquid layer and the gas layer is not very important compared to the first section of our theory. So this part we did not control it because
so you would state that for the levitation itself, the injected volume is not really relevant.
For the Rayleigh-Taylor instability part and the Faraday waves instability part, yes, because we can directly.
There I can actually agree with you that this is not relevant. But further on, there are also some limits and a bit lacking of why the air layer actually forms. And this is, I think, a very important part which needs to become clear in your report on why this air layer actually forms. And in the first place, during the injection of the air, because one would first intuitively think that due to the buoyancy force, the air bubbles would just rise up and there would be no air layer formed. And therefore, I would ask you, can you give me a qualitative explanation on why there's actually an air layer forming?
Yes, because as if I may use the if I may use the pen here. As you can see, when the bubble is injected, for example, here, you can see this part of the liquid has a tendency to fall down to here because of gravity. Do you agree with this?
Due to gravity? No, I don't think it's only due to gravity.
Yeah, of course it's not only due to gravity, but we can just give a qualitative explanation on that.
Yes.
So the remaining liquid on this cross section on the side.
So you would state that only due to gravity.
No, it's not only due to gravity. But if you may let me continue, this part of the liquid has a tendency to fall down. So it causes the air bubble to expand in the horizontal. In the horizontal directions, right? So it eventually forms some kind of whole liquid, whole gas layer, right? And now this now we can like apply our
Yes.
Quantitative investigations on this equivalent.
I agree with you here that this is the reason why the air layers maybe could expand, but my explanation was really in the first place on why this air layer, the injected air, isn't rising in the first place, but rather sinks down, and then we can form an air layer, which you explained quite nice.
Yes, and actually I have done some relevant like quantitative investigations on that. As you can see, the average effect of the oscillation also acts on the buoyancy force. Do you agree with that?
This is okay.
Yeah. So it means that the larger amplitude your oscillation is, the bubble is more likely to like stay here or sink down. However, in our
I must agree with you here. What we really like to see is like the explanation of the effective acceleration, then actually compensating for the buoyancy force, and therefore the air layer could really in first place form here, which you then explained on how this is then actually expanding, and we come to this levitation.
However, I must say that the sinking of the bubbles is not the main reason of the form of the gas layer, because as you can see here, we estimated the critical depth.
It's not the formation of the air layer, but rather why the bubbles actually sink down or stay at this constant height and not just start rising up. And I think this is actually a crucial part which needs to be explained in first order.
In our experiments, we did not observe any sinking bubbles or staying bubbles, because as we did some estimation here,
I would disagree that there are no sinking bubbles. I think the sinking bubbles effect is actually why this air layer actually forms in the first place. But now, maybe since we have limited time, further moving on to another point.
And I must disagree with you on that.
I asked you about, in the clarifying questions, about vorticity free flow.
Actually, I don't quite understand about this concept you just raised, because in our theory, we just we have done our investigations on the regime of a rather small, a linear distribution, and I don't see the significant impact of some vorticity here.
The significant impact of the vorticity flow. So for the this was just clarifying of whether for the Faraday instability you presented to us for your derivation you used this vorticity free flow assumptions, because it is quite popular in literature in order to exceed with this assumption. Therefore, I want to clarify this, because in the most cases from the levitating liquid phenomenon, this is actually not given. But staying on the Faraday instability, can you again show your measurements for the upper boundary?
For the upper boundary, you mean the experimental data? Yes. As you can see here, with our corrected.
Here you presented these correction factors. Why are these physical valid correction factors? Can you please explain this?
Yes, I can explain, because here, as you can see, the n is quite close to 0.5, and we have gave some...
what is the qualitative basis behind this?
The qualitative explanation of this, because the liquid does no longer meet the small viscosity or high frequency liquid limit, so the viscosity term beta may not be directly proportional to the viscosity coefficient mu, but here you can see the depth of the liquid boundary layer on the near the container walls. The depth of it is you can see it correlates to mu to the half power, and you can see when n is approximately 0.5, we can give an explanation that this viscosity term may be proportional to the depth of the boundary layer, and because and that's how you measure the.
And essentially, you then just fitted those corrections which you derived then to your measurements, right?
Yes, we first fitted our corrections, and for the results
So
that
on this part, when you fit the corrections, about your prediction power for the upper boundary layers, how would you state how sure can you predict actually
because
then this upper boundary layer?
we have done the experiments for different kinds of liquids using the same set of parameters we fitted, and you can see there certainly is a certain prediction
Since we are
power.
fortunately out of time, I must stop you
Yes,
before
you
the
have time
chair
for your
does
summary. Thank
and
you both.
start summarizing these discussions. So we first talked about some relevant initial conditions, being the air injection speed, and the volume, which we then cleared up and come to an agreement that this is for the stable oscillation quite relevant, where you showed that it was only one experiment, but we would then come also to an agreement that for the actual levitation effect, the injected volume is not so relevant, and therefore this is applicable in your case. Then we come to the basic explanation and try to clear up why there's actually an air layer forming, why the bubbles aren't rising in the first place, and what does compensate for the buoyancy force. And here we clarified up why this air layer is actually forming, which in our point of view is really crucial, and then for the actual levitation effect. Then we further on came to some assumptions of your theory. And also on the missing predictive power.
Thank you. I'm afraid I have to interrupt you here.
Thank
we
you
have
very
time
much.
for questions from the reviewer.
Hello, my name is Anna, and I would like to ask some questions. First, to the reporter, do you have any phase diagram where both of your limits are displaced? The limit for the ray literal instability, but also for the Faraday wave?
I'm sorry, we did not do that, but yeah, we can easily do if we want.
Can we please go to slide 44?
Yes.
The line that we see is theoretical minimum, right?
I'm sorry, which graph? The left one?
Both of them. Like the blue line is theoretical minimum. Why are some of the experimental data points under this minimum?
Because, yeah, as I said, it might due to some measurement errors. As you can see, they're all within the range of the error bars.
Okay, so experimental errors. I would like to ask whether you changed any other parameters than parameters of the oscillation, which is the amplitude and frequency, and the type of liquid. Like, for example, did you change the surface tension or the
Due
shape
to the
of
limitation of experimental conditions, we did not, but we have done some theoretical analysis on, for example, the size and the shape of the container, which we can show. Yeah.
Okay, then I would like to ask to the opponent, do you believe that fitting the correction factor and its explanation of the physical meaning is valid?
I'm not so sure about the predictive power if you fit your theory to your measurements and then compare to one other measurement row. But generally, I think this is a case when you don't have any other way to describe it quantitatively.
Okay, and I would like to ask, why do you think that the phenomenon doesn't occur or doesn't occur that frequently for larger containers? What's the qualitative explanation of that?
So for larger containers, it's just due to the less stabilization due to surface tension. Then therefore the levitation is actually harder to achieve, and therefore we could see lower as well lower boundaries and lower upper boundaries for larger containers.
Okay, thank you. And do you believe that the vorticity free flow effect is present, and how would you explore this?
I don't think that one can assume here vorticity free flow due to the shear stress on the boundary between the fluid and the actual oscillator, and therefore I wanted to clarify this if this assumption was actually made, because in our point of view it's not applicable.
So is it important?
Yes, as I stated before, it is important.
Then I would like to ask, why is the bubble formation so important?
The bubble formation.
Yes.
I mean, I'm not talking clearly about the bubble formation itself, but rather the sinking effect on the bubbles and then not going up, which is then leading to the formation of the air layer.
Thank you for your answer. And can we go please to this slide? Yes. How was the acceleration measured to the reporter?
How's the acceleration? Yeah, it is directly you use a high-speed camera to track the motion.
So it was tracked.
I'm sorry.
Was it tracked?
Okay.
Yes, it was tracked.
Okay,
Thank you. Then we have time to prepare for the reviewer. 15 seconds.
Hello, my name is Anna, and for Team Slovakia, I'll do the review to problem number 8. We are already familiar with the problem statement, so let's move on to the evaluation of the reporter. First of all, I would like to praise the nice setup with amplifier, frequency generator, and injection mechanism from the bottom, and a high-speed camera, which made it possible to track the acceleration of the container. And I think with this nice setup, a lot of parameters could have been changed, which was really nice. For the boundaries, I really like that he investigated Rayleigh-Taylor instability boundary and also Faraday waves, and there was a good match between theoretical and experimental boundary. However, I think it would be really nice to present this kind of data and boundaries in one phase diagram, so we could clearly see when the phenomenon occurs and when it does not, and actually see when it is possible to levitate the fluid and how this phase diagram would change depending on the parameters of the liquid, for example. I think theoretically this was done pretty well. We could see how the vibration transmitted to the air layer, and we saw the resonance curve, which I think was really nice and fitted amazingly with data. And I think there were a lot of relevant parameters identified, such as the parameters of the oscillation, parameters of the liquid, and parameters of the container. However, what I really didn't like was that these parameters were not changed. Only parameters that were changed were the parameters of the oscillation and 2 different liquids with no clear conclusion, and I think this could have been done better. Also, I missed a qualitative explanation of why the bubble forms, which was then clarified in the discussion, but I would like to see more of the actual stabilization of the layer and why it actually starts to levitate, since I think this was quite sped through. Then I didn't like that the correction factor was not really justified, and we didn't really understand the physical meaning of it. For the opponent, I like that he pointed out whether the shape was investigated and changed, since the reporter said that it has a large effect on whether we can actually observe the phenomenon, and how the air was injected. Was it in the same amount and in the same place? And I think this was quite unclear from the report, since all of it is oscillating and it would be really difficult to actually pump the air from the bottom, so how it was done was clarified. But I really didn't like the answer or the question about the vorticity in the flow. I'm not sure what he meant by it, and a lot of time even in the discussion was spent on this topic, and I don't quite understand why is it so relevant. For the speech, I like that he mentioned the unjustified correction factor and the lack of its physical meaning, and lack of qualitative explanation, and also low quantity of data. But I didn't like that he didn't ask about the changing of parameters and didn't really focus on the stabilization qualitative explanation. He also didn't like the fitted damping and didn't talk about it all that much. For the discussion, I like the topics that were raised. However, I didn't really like the prioritization. First, they discussed the control of the air injection and whether it was sufficient or not, and the opponent thinks it was insufficient. However, I think the methodology was quite good, and it would be really difficult to make it better, since the pumping of the air on the bottom to something that's oscillating is quite difficult to do. Then they asked how the layer of air was formed and sought further qualitative explanation, but this was like a really nice point. However, I think more time should be spent on the actual stabilization of the fluid layer. For the physical meaning of the correction factor, I really like that the opponent raised the questions about this, and we found out that the reporter actually fitted this, but I think the physical meaning of this remained unjustified. Thank you.
Thank you. Final remarks of the reporter.
So yeah, I would like to thank the opponent and the reviewer for their comments, and I'll do some clarifications now. So first, for the physical meanings of the fitted parameter n, here we already explained that we here think the physical explanation is that the viscosity term is proportional to the boundary, to the depth of the boundary layer, instead of directly to the viscosity coefficient mu. And for the for the vorticity free flow, which I think is talking about the effect of the boundary layer. Actually, we have done some estimation that we can see that the depth of the boundary layer is only of the magnitude of the of millimeters, which so the total water it affects because it decays exponentially is far less than the total volume of the liquid layer. And for the size and the shape of the container, we actually done some theoretical explanations. For example, here the container size, and here the container shape. Here we investigated the situation of the square, the circular cross section. And on why bubbles form, here we have done an explanation that is due to the a tendency of falling down of the liquid, and so therefore there will be a tendency for the bubble to expand and form a whole gas layer. And the sinking bubbles, as mentioned by the opponent, is not observed because we can't explain that it is theoretically impossible, that it requires a too large depth. And finally, we'll give an explanation to the whole problem that a oscillation is transmitted to the liquid layer by the gas layer, and with enough amplitude, the average effect of the oscillation can stabilize the levitation. Thank you.
Thank you. Could I ask all three participants to go back on stage, and we'll have some time for jury questions. I would like to remind the jurors that we have a very large jury, so please keep your questions brief and give them a realistic chance that they can answer within like 20 seconds. Okay, who wants to go first? Daniel.
I have a question to the reporter. You said you created your air pocket and then you measured the whole resonance through. How can you guarantee that your amplitude, like the driving amplitude, was kept constant over frequency? Did you check this?
Actually, there's no need to keep the amplitude constant, because in the first section, as you can see here, we measure only the amplitude ratio, and yeah, for the others there are they just need to be measured.
Jim?
So a question to the reporter. Have you checked that your honey's viscosity does not depend on shear rate?
On shear rates, actually, no, but as we are investigating on the condition of a relatively small deformation, so I think, yeah.
Okay.
I think it's quite negligible.
Georgi?
Yep. Hello. So you mentioned somewhere Matthew equation or Matthew type phenomenon. I'm not sure. So please, can you
yes, as
clarify
on
that?
the excitation of Faraday waves, if I may show the slides. Yes, I think, yeah, if the oscillation frequency.
If you just keep the slide.
Yeah.
Okay, that was the question. Yes. Okay. Yes, Andreas. Do we have a microphone? Yeah. Okay.
Yes. Thank you for a nice presentation. There was a lot of discussion about this fitting parameter for your parameter beta and so on, but I was curious already here, in the original expression for beta, k, and mu, do you have it?
Yes, as I may show it here. So
yes. Why is this dissipation proportional to k squared?
This is like from the literature, that under the small viscosity limit, yeah, from this literature, and I have done some corrections because I don't think this fits with our actual liquid. So yeah,
but k is the wave vector, right?
I'm sorry.
K is the wave vector.
Yeah, K is the wave. Yeah, the wave number.
It's an interesting question, but I think we have to move on. Any further questions?
On your presentation, page 21, you show us a fit to a data, and this fit and blue one has those oscillation over there. Can you just briefly elaborate on the reasons of that oscillation in the solution, numerical solution?
You mean this graph? Yeah, this graph. So the accurate solution is made with the first. I'm sorry. This original equation with no like average effect considered, and of course the G is replaced by the effective G considering oscillation, and the yellow line here is using this corrected dispersion relation with the average effect, and I put it here to show that this method is actually quite reasonable to characterize this evolution of the disturbance.
Does any of the jurors who have not yet asked a question have a question?
Can I please again see the slide with the phase shift that goes with the resonance curve?
I'm sorry?
Yeah, you had the resonance curve, the measurement for your air pocket,
yeah,
and there was also the phase shift. Can I see that slide again, please?
Like, yeah, this is...
Yeah, now the phase shift, like delta
yeah,
phi, you had a measurement, yeah, here. Can you elaborate on the deviation of the experimental data from the theoretical line to the left or to the right side? Yeah, to the left it undergoes the theoretical line, and to the right as well. Can you elaborate on this?
Yeah, so this may lead to some like relative minor influences. For example, the friction or the viscous force by the container walls, and there might be some other minor like influences. So it is not a perfect fit, but I think this can qualitatively explain that our modeling is quite reasonable, though.
Clear?
Okay, to the opponent, what is vorticity free flow and why is it that important here?
Okay, so as you already mentioned, he also investigated the depth of the vorticity free flow. So it assumes that there are no vorticities, which is also applicable for the upper case. But when you have this boundary layer with the wall of the side, then you have actually some part of shear stress, and therefore, as you already mentioned, in some depth there are vortices, which when the depth is like comparatively large to the container size, then this is actually a quite hard thing to model in your theoretical model, and also causes some deviations. And I think like the several millimeters in a case of centimeters is hard.
That's clear. All right. Then I think we're out of time. Then I would like the juries to proceed to grading, and I would thank all of you. Oh, danke. We're almost ready, I think. Not quite. Jurors still need to apply some nonlinear transformations. Both are ready? Everyone ready? All right, then I ask you to show me the grade for the reporter, and I will be reading from the left to the right. So show me the grade for the reporter, please, now. 8, 8, 8, 6, 7, 6, 7, 4, 8, and 6. Okay, next the grade for the opponent, please. 6, 7, 7, 7, 7, 7, 6, 6, 8, and 6. Okay, then the grade for the reviewer, please. 8, 8, 7, 8, 8, 7, 8, 6, 9, and 8. Okay, thank you very much. Do you have it? Should we show again? Okay, for the report, we are between an 8. We have several 8s. Can I ask Michael maybe to give a brief comment on? Okay, then this sheet is wrong. I think we have to show the grades again for the reporter, please. Okay, just to make sure, we will show the grades again, and please confirm that you have the grades. I will be not voting, so the first field remains blank. All right, one more time. Grade for the reporter, please. 8, 8, 8, 6, 7, 6, 7, 4, 8, and 6. Can you please confirm? No confirmation? Should we will do the rest too, but can you confirm that you have the grade of the report? It's okay, we can do it again, but okay, for the report is fine. Okay, let's do the opponent again. Oh, so we're done?
Yeah, I think they're good.
You think? Okay, we do it again. Grade for the opponent. 6. Opponent, yes, opponent. We did the reports now. 6, 7, 7, 7, 7, 7, 6, 6, 8, and 6. Okay, that's correct. And then please the grade for the reviewer again. Sorry about that. 8, 8, 7, 8, 8, 7, 8, 6, 9, and 8. Okay, we have it. All right. Yes, the hardest part we managed. All right, then, Claire, could you ask you to give your feedback for an 8 for the reporter? Just some brief feedback, yeah. Oh, sorry. Yeah.
They start with a good theoretical explanation of the phenomena, and also they show the detailed demonstration of how these things levitating. So you start very good, and your flow was very smooth, and there's a quite amount of experimental data which is kind of correlated with your theory. So there's still like nothing that I can kind of pick down. So it was a summed up 8.
Could you just
and
repeat?
my
Yeah.
partial score is somewhere between 4.5 to 5 on the reporting part. Then in the discussion, somewhere between like 1.5 to 2. Then it adds up to 8.
Okay, thank you very much. Georgi, you had a 4?
Georg, first of all, what I did not like in the presentation was that you had many different regimes, and for each of them you had either written down some equations or imported, for example, like Matthew equation and so on, which you did not have time to explain during the presentation very well. So most of the parts where those formulas came from, and for example, why those boundary conditions were valid, why those importations were valid, it was not clear to me. And unfortunately, it was also not explained in the discussion. And yeah, I could not give you high grades in the theory part. Also, there is more minor thing, is the explanation of the phenomenon was done in the during the discussion. Yeah, but however, adding on that, this is a grand final, and like my expectation and my criteria is a little bit compared to a little bit different compared to the usual physics fight. Yeah, so I gave you some cons why I went low, but yeah, this is the grade I give for the first report, and then I just stay.
Could you summarize the partial grades just for the partial grades?
2.25, 1.25, and yeah, 4.
Okay. Could I first ask Daniel to give a feedback for the opponent, and then afterwards Carrie for the 8?
Yeah, I can possibly start with the partial grades. So the questions already gave me the impression that you could have asked for more there, so I ended up with 1. Then with the speech I gave you a 2, and with the discussion it's 1.5, and by the end of the day I rounded up to a 6. So for me, there are a lot of questions. First of all, for the setup, how do we really control the amplitude, and all these graphs with the deviations were just not mentioned, not touched. And that's something you have to do, you must do that. Then there was mentioned that they had like diluted honey. I questioned this in terms of viscosity, and it was pointed out I would have loved to discuss how does viscosity affect the resonance, for example, and then point out that there were not enough experiments done. So that was missing, and then you spend a lot of time on how to inject these bubbles, and that was pointed out. As soon as the bubble is in and we can go through the whole resonance curve, then it's fine with me. So there are more things to do, and start with the obvious ones.
Could you state your partial grades as well? He did, sorry, yes. You did, yes, correct. Carrie, could I ask you for the 8?
Yes, so I'm not miles off from Daniel, but I guess I haven't recalibrated for the final, maybe quite as much. I gave you 1.5 for the questions. I thought they were fairly short and apt. Could have asked more. I liked the speech. I gave that a 3. I felt you covered most of the points, and your time management was spot on. So that pulled you up a little bit. And in the discussion, fairly efficient. We obviously presented your own opinions, and so I gave you a 2.5 for your discussion, and so that came up to 8.
Okay, thank you. Could you also just comment on the review? You have a 9?
Yeah, so the review, I just thought it was really nicely, a nice summary. You asked good questions. So that gave you a 1.7. I really liked the review of the report. You put in, you communicated the points that were made and how well you felt they were important and things really well, and similarly with the opposition. So I gave you a 2.7 for your review of the report, 1.5 for the review of the opposition, and the discussion 1.7. Yeah, I just thought it really helped me to get a perspective of what was going on there. You raised a couple of points that weren't there, and so I really enjoyed it. Thank you.
Okay, thank you. Georgi, can you give a brief comment on the 6?
Yes, thank you. So the only part that I really liked was the clarifying questions. So I went a little up for that. I gave you 1.5 there. With the review of report, it was like I didn't feel like you brought in very much extra, like compared to opponents. So basically, it was more or less the same things. And but like it was there were still some good points, and so in both parts I went on average. And yeah, that's high, a little bit high in the questions asked, average, and that's how I ended up on 6.
Partial grades?
1.5, 1.25, 1, 1, plus 0, minus 0, 6.
Okay. Thank you very much. This concludes the first stage of this final. Thank you all. We will have a 10 minutes break. Please be back in time at 9:33. 9:33. Thank you. All jurors are here. All teams are here. Could those of you who have not yet taken the seats do so as quietly as possible, and then we can have 1 minute for the reporter. Okay, could I have all your attention, please? Could you please? Okay, all right. Please start.
Okay, so I'm Benjamin Graf from Team Germany, and today I'm going to present you our results on problem number 6, dripping faucet. The task says, a leaky faucet develops interesting dripping patterns where the time between drops depends on the water flow rate. Investigate this phenomenon and study how it depends on relevant parameters. So what dripping patterns do we expect here? For very low flow rates, we observe periodic dripping, while for higher flow rates, there are other dripping patterns, where no regular pattern can be observed by the human eye. The most important parameters affecting the system are the radius of the nozzle, as well as the most important parameter, the flow rate. For the water, the surface tension, as well as the dynamic viscosity and the density are relevant parameters, which are all varied by the temperature. We'll begin by explaining the different dripping patterns before analyzing the droplet dynamics more in depth. In the end, we will investigate the limits and the transitions between different phases. As dripping patterns, we look at the time between 2 consecutive drops. This time Tn is the state variable of our drops. We then plot 2 consecutive time intervals in a so-called return map. For example, when all the points are clustered around the diagonal, we observe periodic dripping, as all time intervals are roughly equal. Going on to explaining this dripping, we need to look at the dynamics of the drop. During its build-up, surface tension dominates gravity. That's why the drop is still attached to the faucet and remains stable. However, as soon as a critical volume is reached, surface tension balances gravity. So this is the maximum volume that can be held back by surface tension. As soon as this volume is further increased, gravity exceeds surface tension. The drop cannot be held back anymore and detaches. As the remaining water at the faucet snaps back, it oscillates. The next drop is then critically affected by this oscillation and in this way dependent on the previous drop. That's why higher periodicities and more complex dripping patterns might occur in the system. As we've already stated, we have the limits of very low flow rate with periodic dripping and higher flow rate where interesting dripping patterns may occur, and also a transition to jetting. Here you can see the overview of the following report. Let's at first begin with our experimental setup. A laser was used in order to measure the time between drops. To measure at a constant flow rate, we used a syringe pump and also checked the accuracy and constancy of it. For continuous flows, we used a second setup, with which we can vary the flow rate slowly or keep it constant. Here, a video analysis was used to measure the individual droplets. We separated the foreground using a binary threshold and detected the contours using OpenCV. Each drop was sliced in disks of 1 pixel height. Assuming that each disk is circular, we can easily calculate the volume and the center of mass of each drop. In order to increase our accuracy, we interpolate the trajectories quadratically. Using this method, we can increase our resolution from 1 frame per 8 milliseconds to a precision of around 0.2 milliseconds. We also varied the surface tension using different liquid soap mixtures and obtained a reference curve using the ring method. Coming to our preliminary observations, we observed the intuitive periodic dripping for very low flow rates. However, when we increase the flow rate more and more, different periods are visible. So here we are in the quasi periodic regime. For very high flow rates, there are no real patterns observable. We are in the chaotic regime. Moving on to the investigation of these individual dripping regimes, we begin with the periodic dripping, occurring at rather low flow rates. Here, the drop fills up slowly. As soon as the critical volume is reached, the drop detaches. So by predicting the critical volume, we can also predict the time between individual drops. In order to predict this, we'll model the surface of our drop. We'll at first parameterize our drop using the z coordinate and its radius, as well as the height, the arc length, and the angle. And then we can state two quite geometric parameterizations, and using the Young-Laplace law, we can derive the last differential equation stating a complete ODE system. Every boundary condition for this is known, except for the height. So we look at the different possible combinations of volume and height and see that for one height there are multiple possible volumes. However, only the first branch here is stable. The maximum volume possible is therefore our critical volume. Comparing this to our measurements, we can see that the shape matches quite well. But this panning drop is not always quasi-static. After one drop detaches, it oscillates. But in this case of very low flow rates, the oscillation damps out completely before the next drop detaches. So the next drop is not affected by the previous one, and we observe periodic dripping. In order to measure these periodicities, we varied the radius of the nozzle and measured the dripping intervals for many different flow rates. Here, each point is an overlay of more than 100 individual droplets. You can see how exact their periods match up, as we are here in the periodic regime. Plotting our theory through the measurements, we can observe an almost perfect agreement without any fit parameters. As expected, a higher radius leads to bigger drops being able to held back by surface tension and able to form. Similar measurements have been done for varying surface tensions. Also here we can predict the results quantitatively. As a higher surface tension can hold back a bigger drop, the critical volume and with it the detachment time increases. So now we've fully investigated periodic dripping and predicted it quantitatively. So now let's move on to the second phase, which is the quasi-periodic. In this regime, double period patterns and simple periodic regimes alternate. However, we note that the return map is mostly symmetric to the diagonal. When looking at how these droplets are formed, we see that the drops no longer detach completely regular, but rather in a drip-drip, drip-drip, drip-drip pattern. These two different sized drops correspond to the different branches in the return map. But why should we expect different periods? After one drop detaches, we see an oscillation, as seen previously in the periodic regime. However, here, this oscillation does not damp out before the next droplet detaches. So the next drop is critically affected by the exact phase of the oscillation caused by the previous drop. Because of these interdependencies, we observe quasi-periodic patterns. So what we need here is that the time between drops is in the same order of magnitude as the oscillation time. When zooming in, we can see, and looking on such an interesting pattern, we can get a first hint of a possible fractal attractor in higher dimensions. So now let's move on to the chaotic regime. As with the previously seen period doubling cascade has already shown that the system is very sensitive to its initial conditions. This gives a first hint to chaos that may occur for higher flow rates. When zooming into this region, we indeed observe a transition to chaos, as this return map is not really symmetric to the diagonal. Zooming in on one individual part here, we can see that there are two rather enclosed areas hinting at two branches of the higher dimensional attractor, of which this return map is a slice. To really prove that chaos is in the system, we'll use the Lyapunov exponent. The Lyapunov exponent describes the divergence rate in the phase space, and as soon as it is possible, is positive, the trajectories diverge, and we indeed observe chaos. For approximating it, we use the Rosenstein algorithm, of which we can calculate the Lyapunov exponents out of our experimental data. We begin with multiple points very close to each other and look at their trajectories through the phase space, of which the return map is a slice, as previously mentioned. Plotting the mean divergence and linearly approximating it, we can see that they diverge indeed. As we have obtained a positive Lyapunov exponent, we can safely state that the system is chaotic. We also plotted the Lyapunov exponents for different flow rates, and as we expected for rather low flow rates, the system is periodic. So here the Lyapunov exponent is negative, and we don't observe any chaotic pattern. However, when we increase the flow rate more and more, chaos becomes more and more visible as the Lyapunov exponent grows. So now we've fully investigated all three phases. But what happens in the limit of even higher flow rates? When increasing the flow rate more and more, capillary forces holding the drop together might be overcome by the effects of inertia. Looking at the ratio, we introduced the dimensionless Weber number. If this number is exactly 1, we are at the border between jetting and dripping. These capillary forces can only hold back the drop volume if the inertia does not push too much on it. Otherwise, the capillary forces only act from the side of the jet. Looking at the experimental results, we can indeed observe this transition. However, note that there is a hysteresis present. This transition can also be predicted quite accurately by our Weber number. Looking at the jetting regime, we may encounter the so-called Rayleigh plateau instability, where individual modes might grow and disturb the jet. The fastest growing mode then determines the jet breakup, which will indeed form new droplets. This Rayleigh plateau instability is also encountered in the neck, holding back the drop very slowly before it detaches. This neck breaks up due to Rayleigh plateau instability too. So as we can see, when this drop detaches, satellites are formed, and the radius of these satellites corresponds to the fastest growing mode. So the previous drop is split in the pennant drop, the satellite droplets, and the main drop. These satellite droplets can also be observed in the bifurcation diagram previously investigated. So now that we've covered the preliminary analysis as well as the dripping regimes and had investigated some edge cases, let's summarize the report. We had a sophisticated experimental setup with an optimized video analysis providing subframe accuracy. We fully investigated the periodic dripping and had a qualitative theory for the phase transitions. And we investigated experimentally all the three dripping regimes, varied the outlet radius as well as the surface tension, analyzed the chaos. And with that, I want to thank you for your attention.
Thank you. questions from the opponent.
Good morning. My name is Jakub Niemczyk, and I will be the opponent for Slovakia. So my first question is for your graph, where you have shown the periods you have calculated for periodic dripping. Can you please clarify how did you obtain from your numericals, I think, approach, like what is the critical volume of the droplet?
Well, we've seen this here. The critical volume is the maximum volume possible for the stable branch. Then out of this critical volume, we can calculate the time
Okay,
between
thanks.
blocks as previously shown.
Also, what is the error on these graphs?
We did not calculate it, but it is visually observable that they fit quite well.
Okay, thanks. Can you please go to your Pointer return map?
Which return map? We presented...
Slide 40.
Slide 40, okay, yeah.
So, did you change the flow rate here?
Yeah, exactly. We did change it, but in this region here, it is so constant that we can safely assume that it is quasi static.
Okay, thanks. Can you please clarify whether you have any theory for the dripping pattern? So you had a lot of complementary calculations, such as the periodic behavior, or for the jets, like whether do they form, but you have actual theory for the periodic pattern, for the maybe chaotic patterns or something like that?
Of course, we can talk more in depth about this in the discussion. However, we have some qualitative model and could present how a quantitative model could be modeled in order to predict this phase transitions.
Okay, thanks. We can return to this in the discussion. Can you please show me your slide where you calculated the Lyapunov exponent?
Yeah, of course. Do you mean this one here?
Okay, so I have two questions. Firstly, did you always fit the curve on that part of the measured divergence?
Yeah, exactly. As we have so many points here,
thanks.
This part is really the one where you should fit the Lyapunov exponent.
All right. Could you please start?
Hello, I'm Jakub Niemczek, and again, I'm the opponent for Slovakia to the problem number 6. The problem statement is, a leaky faucet develops interesting dripping patterns where time between drops depends on the water flow rate. So investigate this phenomenon and study how it depends on relevant parameters. Now, and this is quite important, the relevant parameters. So let's look at what the reporter has done. He came up with a very good qualitative explanation where he talked about how the droplet forms, and there is this like residual volume oscillation effect on the droplet drip, and he talked about the different regimes which happen here and like the surface tension that is keeping the droplet together or whether it falls apart. Furthermore, he developed his theoretical model for periodic behavior, and I really appreciate this, that it matched well, and I also appreciate that he came up for theoretical model for like many complementary things, and he also tried to calculate the Lyapunov exponent. However, I think that for the actual important part, which is the chaotic behavior or maybe the splitting periods or something like that, he didn't even come up with a theoretical model. So that is something that is something I would expect, and I would really appreciate that. Furthermore, he showed us this return map of the patterns. However, the flow rates changed during this return map, as we could see. Maybe we can talk about this at the start of the discussion. And also, he had some big experimental own contributions. So I really liked how he, using OpenCV, he, I think, tracked the droplets, their size, and what is the flow rate. And he could even find out, of course, what is the size of the droplets. He had many repeated experiments, and he had quite a stable apparatus. However, I think what he used to measure the flow rate is that his setup was decreasing the flow rate, and over the time he was measuring these the flow rate. So I think that maybe he should have come up with a exact flow rate for each measurement and not have a continuous movement, in my opinion. So he explained trends on his graphs. He came up with some qualitative understanding of this, where he told us, we had this oscillation, this residual oscillation, and he tried to connect this with his Poincare return map. I really liked that. I really appreciated that. However, still the Poincare return map was quite unclear, because we could see that it is like a growing, where we could see that the greater the period of the previous, the greater is the period of the next droplet falling down, and also for the small periods, the droplet sizes were greater, so obviously the flow rate was changing. Now, for the interesting dripping patterns, we could see on his graphs that he observed for the different flow rates what they were. It was unclear to me that, we could see this this decreasing curve of flow rate versus the dripping period. However, in this curve, we couldn't really see what he said. So, for example, there were some places in his regime which he called is period doubling, but actually there was just a singular point in that flow rate. So it seemed like for that exact flow rate, although it was in the period doubling regime, there was only one period present. So overall, I really liked this presentation on the experimental approach. He tried to vary some things. He had a good setup. However, the theoretical prediction of the actual patterns was lacking, and also the Lyapunov exponent calculation.
Could you proceed to the discussion, please?
Okay, so yeah, for the Lyapunov exponent, can you please clarify how did you use the Rosenstein algorithm?
So what we did is we sampled multiple points in a very small region in the phase space, and then we plotted their trajectory through the phase space, which is here represented by the return map. Then looked at the mean divergence of these multiple trajectories and plotted it and fitted the linear fit through its logarithm, and by this obtained the Lyapunov exponent.
Okay, so I have several questions about this. First up, what was your embedding dimension in your Rosenstein algorithm?
Like here we have only these two dimensions, as we use only Tn and Tn plus 1.
Okay, but I see you cited the Rosenstein paper about calculating the largest Lyapunov exponent.
Yeah.
So what the Rosenstein algorithm does is that it embeds the data onto like vectors of maybe, well, usually it's 2 times the number of degrees of freedom plus 1. For example, that was for the magnetic gases problem. And then from the divergence of the closest vectors, he calculates the
May I
Lyapunov exponent.
shortly add that in my opinion, the degrees of freedom in this system may even be infinite.
Yeah, I agree with you.
So I think
therefore, that's what I'm asking. So what is actually the embedding dimension you have used in this system?
As I stated, we used Tn versus Tn plus 1. But as this Rosenstein algorithm is designed for these discrete time series, I think that indeed this two-dimensional embedding of the high-dimensional attractor is indeed valid.
Okay, I think I disagree with you. I think that you should have used a higher like embedding dimension.
So you
but
would,
my main problem with this is the is how you fitted the divergence rate. So can I please state what I think about this graph? Well, we can see on this graph that at first the divergence is exponentially rising. So this is the chaotic behavior. This is when the distance between the two close position is like exponentially increasing, and then the graph is about constant. So the reason why the graph is about constant is, in my opinion, because, well, there are some like constraints to this system, and you cannot like infinitely change. So they're as like different as they can be. And for this reason, the correct way to fit the curve would have been at the very beginning of your graph, in my opinion.
I don't fully agree to this. I see what you mean, but however, I shortly want to clarify that we are not in the regime of transient chaos here. We really have pure chaos, so it's not like that chaos only occurs in the first phase. However, I understand what you mean with the limited attractor, but we think that as we have this, we only use these data points, and as they are limited by themselves, we think that this point is indeed where we should stop. And I would really like to mention that we are on the logarithmic scale. So this is not the only part where it increases exponentially, but it is increasing all the time. So I don't think that it has reached the limit of the attractor.
I disagree with you, and I think that you should have fitted it in the beginning, but let's agree to disagree and continue on another topic. So do you have actually a theory, as you have mentioned before, for the actual dripping patterns? That would be the split period, or that would be the chaotic patterns?
Of course. Do you want me to begin with the qualitative or the quantitative?
Yeah, do you have a quantitative theory?
A quantitative theory. So how we could model this is we take this drop, we slice it in individual disks.
So did you do this?
No, but but I would like to explain how it works, or I can show you our results on the qualitative model.
Okay, you can show me how it could possibly work.
Okay, of course. So then we take every individual droplet, every individual disk. However, we have to use some assumptions here. One of the most important assumptions is that the velocity of each particle only depends on its vertical coordinate. And I think that this assumption is indeed not really applicable, and that's one of the reasons why we did not model it. Another reason is that it is very hard to model this because the number of generalized coordinates on which our ODE system acts here is the number of slices.
Okay.
This number of slices changes constantly as we increase the volume. And as a third point, I think that the breakup, which we would model here, is that it breaks up at a at a critical radius. And I think that this critical radius cannot be determined really with a physical insight. So I don't think that this quantitative model would give any physical insights, as we can predict the droplet shapes itself. We have obtained the Lyapunov exponent, and so
I think I disagree with you on this, and I think that you should have at least tried this, maybe shown us what would be the results. But I think we can move on to another.
Where we do have results is for the qualitative model. Here you model the...
So this is the same thing, right?
No, it's not the same thing. What is the essence of the dripping faucet problem is that you have this drop, which constantly changes its mass, and it's pulled up by surface tension.
Okay,
so how we
I
would
understand.
qualitatively model this is with a spring and a constantly changing mass. And this spring represents the surface tension, while this mass, which is constantly growing, represents the drop volume. As soon as this mass exceeds a critical point, a part of this mass is separated, it snaps back, oscillates, and we can observe like qualitatively agreement between the two regimes. However,
I agree with you that here we can see, well, maybe some qualitative agreement, although it looks like quite a lot different. And maybe you should have included this in your presentation, but as we are like digging maybe too much on this theme, we can move to something else. I think that you should have tried out this model in order to measure qualitatively.
I think we have presented many reasons why this is not
can we
really
please go to the
giving
graph
any
with changing flow rate?
You
have
mean
a
the
period
bifurcation
versus
diagram
flow
or
rate.
the return map?
Something like the one you have on the right, but you had it in your presentation.
Yeah, of course. I can look it up. I think.
Slide number 40.
40. Thanks for the help. Are you sure it's slide number 40 or is it rather the slide?
No, this one.
Yeah, exactly. Okay.
So maybe to clarify, am I right that this is the periodic regime?
This is periodic.
This is split period, and this is chaotic, right? So, for example, like right above me, there is this place which is in the chaotic regime, there, where we have just single period. Why do you, like, how is this possible, as you say that this is a chaotic regime?
So I would like to draw an analogy to the logistic map here. The logistic map also has this bifurcation into chaos. We also encounter a period doubling cascade. But in the chaotic regions, there are points where we indeed have periodic regimes. And this is what I think occurs here. We can also draw an analogy to what is happening here, where we only have periodic drops. What is occurring here is that the case of the crazy periodicity is the oscillation. And
okay, so do you have a qualitative explanation why this is happening?
Yeah, exactly. I'm about to explain it. And as soon as this this oscillation is exactly in phase with the time between the drops, it is not critically affected by the drop before. So the next drop detaches every time at the same phase. We can even, if you want me to prove
okay,
this,
so I think I agree with you on this. And okay, again, this is the same as with these things you have shown us. Maybe you should have included in the presentation.
I think that we've quite well seen it in the qualitative model. I agree on this. Yeah.
So yeah, let's move on to maybe the last thing we will cover. We'll see how much time we will have. So can you sum up, like, what are the parameters you have changed? Because actually, if we look at the problem statement, there is, how does the dripping patterns depend on flow rate, and this like graph, how does it depend on relevant parameters?
So what?
Yeah, but this is not for the interesting dripping patterns.
Okay, so you ask for the interesting dripping patterns. Give me like really short time. I'll just look it up. So yeah, it works. And then we, okay, so we varied the radius and we observed that for, I'm sorry, the plots are currently not working. I can pull them out afterwards. We have technical issues here, but what we observed is that for a rather smaller radius,
I'm afraid I have to stop you
the
guys here.
chaotic patterns occur later.
Thank you. The opponent has 1 minute for a summary.
So thanks to the reporter for the nice discussion above the presentation. I really appreciated some parts of it. However, during our discussion, we have talked about the Lyapunov exponent, and well, I think the reporter didn't really understand how he calculated his Lyapunov exponent. He couldn't clarify the embedding dimension of his algorithm. What was like, why was the fitted curve fitted where it was fitted? Because I disagree with that, and I don't think that the methodology of calculating Lyapunov exponent was like completely correct. Furthermore, we talked about the theoretical model for interesting dripping patterns, and well, the reporter explained how he should have done it, but he actually haven't done the quantitative one, and he showed us some qualitative model. We didn't really have time to like completely clarify it, as this would probably take a long time, and we already spent a significant part of the discussion on it. He should have included it in the presentation. Also, that was for the changing of parameters on the interesting dripping patterns, which we didn't see at all.
Thank you. Questions from the reviewer?
Hi.
Can we restart?
Thank you very much for your report and the discussion. Firstly, can I check what's the faucet radius you used on your first slide?
On the
could you go to your first slide, please?
Sorry, I think it would take quite some time to go to the first slide.
No, just press 1 and enter. 1 and enter on the keyboard.
No, I'm sorry, I am in another presentation, but the faucet radius was about 8 millimeters.
Okay, what kind of faucet did you use? Like what material?
We used different faucets, 3D printed faucets, home faucets, as well as metal ones.
Okay, have you investigated using an ordinary faucet instead of like a...
Yeah, we did.
Okay, what's the wall thickness that you used for this video, like in this video?
You mean the wall thickness of the faucet itself?
Yes.
Here the wall thickness is about 3 millimeters.
Do you think this is like very good? Do you think it's too thick? Like the adhesion between the water and the wall be very significant opponent? What do you think?
Can you please...
like because they said the wall thickness is 3 millimeters, do you think the water wall adhesion will be significant?
I didn't see... I think yes.
Can I just add on this?
Sure,
I think that adhesion is not the relevant problem, as the breakup does not occur at the faucet. However, I think that the radius of the faucet is here not constant. That's why we only use this for qualitative insight and not for quantitative investigation.
Yeah, but also...
wait, it's fine. I think the contact angle is not controlled for, but anyway, we'll move on. Can you go to slide 7, please?
Slide 7,
yes,
of course.
The drop doesn't look like it properly adheres to the full faucet. Do you take any precautions to ensure that it does? Here, see, look in the video, it doesn't look like it completely adheres to the full faucet and it's slanted to one side. Do you take any precautions?
You mean that it is anti-symmetric?
Yeah, look, you can clearly see that it's not like...
As we've stated, this was not used for quantitative prediction, but only for qualitative.
That's fine. Can you go to slide 20, please?
Sorry, which slide?
Slide 20.
Yeah, of course. Just begin with
I think that the red periodic regime still looks quite chaotic. What do you think?
I think that this is rather noisy.
I see. Opponent, do you agree with their assessment?
Well, I think that this regimes is completely wrong, because he has also periodic regime in his split period. Also in what he called chaotic regime, he has a periodic movement. So I think that this whole classification into these 3 regions is incorrect.
I see. Thank you. Can you go to slide 9? Your Dunoy ring setup to characterize surface tension. Do you characterize the surface tension for normal water as well?
Sorry?
Do you get the value for normal water as well?
Yeah, exactly.
So what's the value?
It's 72 million Newton per meter.
I see. Can you go to the surface? So you decrease surface tension to 1% of its actual value, and the dripping periods are about 2 seconds to 6 seconds. Can I just confirm that?
Yeah, of course.
I see. Okay, that will be all. Thank you.
Thank you. Okay, can I ask the reviewer to start?
Good morning, everyone. I'm Jonathan Huang from Team Singapore, and I'll be reviewing problem number 6, dripping faucet. Now for the report. The strengths, they had a good experimental setup where they used an LED array for uniform lighting. They used a camera to track the dripping and the drop volumes, and they used interpolation for subframe accuracy, and I think this is very good. Next, they explain the chaos when the phase of the previous drop affects the breakup of the next drop. And I think that this is a good explanation for the chaos, and that they investigated the dripping to jetting transition as the limiting case of the phenomenon, which occurs when the Weber number is 1 or above. I think that this is good as it explores the limit of when the dripping occurs. And they use a return map to visualize the chaotic attractor, which governs the interesting dripping patterns. Because this highlights that the dripping is not stochastic, but it's dynamically governed. So the shape of the chaotic attractor on the return map will not be some random blob of points, but rather there will be some structure to it, which they have investigated sufficiently, in my opinion. Now for areas of improvement, they use a non-uniform 3D faucet, which is very thick, and their experimental pictures actually show the asymmetry of the drop hanging from the faucet. And because their wall thickness is also very thick, this leads to an inconsistent contact angle that is very hard to account for theoretically, and I believe that it will be very different for different runs, so your results might also be different. Next, the theory only solves for the equilibrium drop shape, which is derived from the static force balance, so it cannot predict the pinch drop or chaos, which I believe is very important. And there were also certain discrepancies in the regimes observed, such as the chaotic windows in the periodic regime and vice versa. And they also incorrectly implemented the Lyapunov exponent in 2 significant ways, which the opponent has pointed out, and that their static stability analysis and jet breakup is not actually relevant to the interesting dripping pattern. So I believe that the prioritization is a bit off in this case. Now onto the opponent. I believe that they rightfully pointed out the limitations of the static model, which is that it has no rebound, which is the source of the chaos as the report acknowledged, and thus it cannot predict the interesting dripping patterns in the problem statement. And they also pointed out the incorrect implementation of the Lyapunov exponent, both in the embedding dimension, which means that, for example, for a 3D shape, if you only take the 1D projection, the shapes might be completely different, but the 1D projection will look the same. And thus, this is the same mistake that the report is actually making, as well as the divergence in the first few seconds. And they also correctly pointed out the discrepancies in the regimes observed, which I think is very good. However, they had an unclear discussion on the regime classification, such as the periodic intervals in the chaotic points and so on, and the period doubling cascade. And I believe that this could have been further clarified by comparing it to the logistic map and seeing that it does not actually evolve in the same way. And there were also lack of suggestions pertaining to experimental controls, for example, the faucets. And I think that I think they could have further clarified the qualitative explanation for the chaotic dripping and the non-uniform 3D faucet, because this affects the adhesion and the inconsistent contact angle, and I think it's quite significant, as well as the surface tension's seemingly non-existent effect on the periods, because at 1% of surface tension, the periods are still 2 to 6 seconds. And I think that the critical volume should be reached about 20 milliliters per meter. So I think that this is quite significant. They discussed the incorrect implementation of the Lyapunov exponent, and I agree with the opponent that even in chaotic systems, the divergence in phase space will plateau after reaching the bounds of the energetically accessible phase space, and that they should not take the t equal from 0 to 1,800 for their Lyapunov exponent fit, and it should be for the first few seconds, and the embedding dimension is also wrong, as given by Tegan's theorem. Next, for the dynamic model, I agree with the opponent that the dynamic model is very significant because it can predict interesting dripping patterns, and even if the reporter does not believe that the mass spring model is accurate, I believe that they could have implemented it for qualitative predictive power, and that on the regimes, period doubling is not actually observed because it's completely different between the logistic map and the dripping faucet system, and the opponent also rightfully pointed out the other discrepancies in their data. So in conclusion, the reporter qualitatively discussed chaotic dripping as due to rebounds of past drops affecting the breakoff of future drops. They modeled the system with the static force balance, and the opponent rightfully pointed out these limitations and the incorrect implementation of the Lyapunov exponent. So I believe that because they cannot predict the chaos in the system, I believe the reporter has not sufficiently answered the problem statement. Thank you.
Thank you. Final remarks.
Thank you. However, I think there were some misconceptions. As a first thing, I want to mention that we actually implemented the qualitative theory and we had qualitative prediction power. As a second point, I want to focus that the Lyapunov curve was indeed obtained correctly, as the x-axis was not representing seconds but samples. So I think there was a misconception between the reviewer and us. Going on to periodicity occurring in the chaos, we think that as the system is really sensitive to the phases which were of the previous drop, we think that they really occur periodicity. And the analogy to the logistic map was only meant qualitatively. You shouldn't understand this as we see a period doubling up to like periodicities of 16 here. We also think that the non-uniform 3D faucet was 3D printed faucet was a misunderstanding between us two, as the faucet you focused on in your clarifying questions was actually a normal home faucet, which was, as I stated, not used for quantitative investigation, but only for qualitative. The 3D faucet has really thin walls, so I don't think that the contact angle here is important. We also want to answer to the concern raised that the flow rate was not kept constant. We varied the flow rate to really display the dripping patterns and, as you stated, show the periodicity in the crazy periodic and chaotic regime. We define the chaotic regime as a regime where chaos may occur. However, as already known from other systems, there are regions where really periodicity also occurs in chaos. We also left the flow rate constant for measurements where we really want to resolve the attractor. So I think that this changing flow rate has no significant impact, and we proved this by keeping it constant for individual measurements. However, I want to thank you for this insightful fight, and really thanks to both the opponent and the reviewer.
Thank you. Georgi.
Thank you. Can you go to the slide where you calculate Lyapunov exponent?
Yeah, of course.
And you will do. So why do you calculate Lyapunov exponent from like 0 to 750, and for example, not from 0 to 500, 600?
I think we sufficiently focused on this in both the discussion and the review. This is because this is of our limited data. We think that this is indeed the period where we want to calculate this. We see that it has not reached the limit of the attractor here, as it is still exponentially increasing. So we don't think that the limit of the attractor is reached here, and we do think that our Lyapunov calculation is indeed valid.
Thank you.
So a question to the reporter. I saw you have two systems, a laser system and a camera system. What is their time resolution, and how does it compare to the spread of your data in the periodic?
Well, for the camera system, I stated that we increased the resolution from, we had a sampling rate of 1 frame per 8 milliseconds, but using our subframe accuracy in the period region, we had a standard deviation of only 0.2 milliseconds coming from both experimental noise and measuring imperfections. So we think that the subframe accuracy really increased this quite high. For all the return maps presented, we also used the video analysis.
Mihai?
Thank you. You've shown us this spring model. Do you have any written equations or at least proportionalities to describe what is behind this model?
Well, I just have to look it up, but I do have... just go on, we'll bring this up later. We have to search for it.
Okay, can your colleague find it? And then Daniel has a question.
Yeah, of course.
I have a question. You, for a very short amount of time, showed us that you had quite a lot of satellite droplets.
Yeah, exactly.
Just cut off. Did you think about reducing them, and would there be a chance to do that?
I think it's an active field of research to construct a faucet where no satellite drops occurs. You really have to make many changes to the faucet to avoid satellite drops, and we think that this is indeed something interesting, so we didn't optimize our setup to reduce them. However, we observed that for lower flow rates,
quick follow-up.
Yeah. A follow-up then, did you always measure with soap solution?
No, for most of the measurements, we used pure water.
Okay. Michael?
Yes, I would like you to go again to slide number 54, please, if it's possible.
Okay, we'll just, sorry. Okay, thank you.
Okay, on the right side, you got several yellow dots. Why didn't you take them into account at all?
No, this is just qualitatively explaining how the Rosenstein method works. These are not actually the trajectories which are plotted. However, this is not something that we do, but the Rosenstein algorithm simply samples the nearest point in phase space.
Thank you.
Do you have the model ready to show?
Sorry?
Can we go back to the previous question of Mihai?
Yeah, of course. Yeah, here the model for the spring model is.
Which part shows us this doubling effect? I think that was also...
I think that this is not like, this is a numerical method, so we don't have an equation, but we solve this iteratively. And as we've stated, the cause for the doubling is that the remaining thing oscillates. And this is given by by this oscillator here, so we don't have a real equation showing this periodicity.
Clear?
Okay, to the reporter, how did you actually measure the time with the laser? I mean, laser is a finite beam width, and your drip is like different by shapes, and like it's not even symmetric. So, where is your like a time of arrival corresponding to your drips?
Well, I
different drips.
Well, I think that you're talking about that the drop goes through the laser through a non-infinitesimity time. I think that it's not really important when we measure the time, because the time where the drop goes through the laser is negligible compared to the time between drops.
Okay, last questions from Viti.
Okay, on slide 20, you said there was noise in the periodic regime. On slide 20.
20. Yeah, okay. I think it's the same plot, but I can go back to slide 22.
Yes, you said there was a noise in the red regime, but I see no noise on page 37, which is the same plot in the same regime. Why is that?
And no, this is a completely different plot. This is measured only for the periodic regime. And here we also plotted Tn versus the flow rate. However, what we would like to show here is surface tension. And these are different measurements.
All right. Okay, I think we're out of time. Can we please proceed to grading? And thank you all.
Good job.
Claire is done. Jim, you done? Tomasz, also done? Mihai? Yes? done? Almost. Okay. VT, are you done as well? Does it go faster if I look? Sorry. Daniel, you're also done? Georgi, yes? 1 second. We still need a minute. All right, we are ready. I will start with Claire as the first grade. I'll read it then to the left. Okay, the grades for the report, please. 5, 7, 7, 6, 7, 5, 5, 5, 7, and 6. Okay, all right. Next grade for the opponent, please. 6, 7, 6, 6, 8, 6, 8, 7, 7, and 7. Okay, all right. And finally, the grade for the reviewer, please. 7, 7, 9, 7. Sorry, I start again. 7, 9, 7, 7, 7, 7, 10, 8, 8, and 7. Do we have that? Okay, all right. We start with a justification for the report. We have several 5s and several 7s, but still I think we give a feedback for the student. Claire, may I ask you for the 5?
Yeah, well, I think it's really nice that the reporter kind of divide the different regions of the mechanisms. So that's a good start. But then again, I have a big problem with your time measurement and your explanation about your experimental procedures, because I think that the accurate measurement of time is very essence of this problem, because if you're doing with a laser, then the accuracy heavily depends on the size of the drips. And for example, like in between, like a transition period from the periodic region to the chaotic region, in between, I think there's a bunch of different, the various patterns might form, but somehow your data doesn't show that, probably because of this time measurement. And also the chaotic behavior is one of the parts of this problem, but I don't think that's the major part of this problem. You should talk more about the periodic pattern or the different drip patterns, rather than spending lots of time on the chaotic on both opponent and the reporters.
Okay. We also had one of the 7s. Could I ask you here to give a brief statement?
Yeah, so I thought, in general, you talked about all 3 of these regimes, which I very much like, and I do share a lot of opinions with Claire in that I thought it would have been even better if you can talk more about the instrumentation. You only talked about the camera side, but then you also mentioned the laser side, which we didn't get a lot of information about. And I think I saw a little bit of inconsistency between the graphs, between how much the spread is in the data set between what you claim to be the periodic regime. So I thought maybe spending some time to clarify that would have been better. So my partial scores are the beginning 1 plus 5 for the report, plus 2 for the discussion, and then minus 1 for the question. So that leads to a 7.
Okay, thank you very much. For the opponent, Andreas, can I ask you?
Yes, I gave an 8 for the opposing team. I liked the discussion very much. It was maybe a bit too long on the Lyapunov bit, but what I really appreciated was that we finally got to learn that the reporting team actually had a qualitative model, and that was something I wish you would have shown, and I think you brought up a lot of important points.
Okay, could I also just briefly for the partial grades?
The partial grades.
Yes.
So I have given 1, 1, 2.8, 2.7.
Thank you. Tomek, for the 6, I think?
Yes, I gave you 6, and I will start with explaining the partial grade. So I gave 1, 1.75, and 1.5. And for me, the discussion was actually led by the reporter. So that's the thing that I have noticed, that you really wanted to ask many questions, but when the reporter has to talk, he was really putting things clearly and answering all your questions and having very confusing. You were very confused by the answers of the reporter. And I also noticed that you brought this Lyapunov exponenta into the stage, but that was not elaborated in a proper way. And then also you did not notice the different units of the flow rate used by the reporter. I think that's
partial grades as well.
I already
at
the beginning.
Sorry, I'm tired. Then let's move over here for the review. Daniel, can I ask you?
Yeah, so I start with the partial grades then. So I gave you 2 in the questions, 3 for the review of the report, 2 for the opposition review, and then in the discussion 1.5 and 0.5 for the missed physics. So I ended up with 10, and I'm actually happy to be able to show that 10, because I think what you have done is such a lot of things, and you pointed it out in a very good way. But I have to say, towards the end, it was just too fast. And I could imagine that you have a lot of points being deduced because of being too fast, right? But I could also follow the slides and I read it to see the points. And I think I just ended right at the 10 due to the fact that you are really, really, really fast. But I didn't take points away.
Okay, Michael?
Yeah, my partial grades are 1.252, 1.251, and 0.25, so I ended up with 7. And it's exactly what Daniel said now. I deducted some points because it was too fast and very hard to follow. So compared to the other review, for instance, where we also got very good new insight, where I could follow quite well and understood what they were talking about. And here I struggled a lot with getting your points and had to read a lot within this time. And that's why science communication was not very well done, in my opinion, although you brought up lots of very good points. Yeah.
Thank you. All right, this concludes stage number 2. Thank you all. We'll have another short break and be back at 10 to 11. Can we have 1 minute preparation time for the reporter, please? Could you please take your seats quietly, and then we close the doors. Can we close the door, please? Could you all quiet down a bit? Excuse me, can we close the door? Sam? Working on it. All right, then please start.
Hello, my name is Luizela Lavrikova. I'm from Team Slovakia, and this will be our report of problem number 5, dancing slinky. So for the problem statement, twist a slinky several times and keep its bottom fixed. After releasing the top, the slinky starts to dance. Wave-like phenomenon can be observed from the side view. Explain the phenomenon and investigate the relevant parameters affecting the slinky's motion. So here's the phenomenon demonstration. We turn the slinky NT times and we observe the wave-like phenomenon where the slinky sort of torsionally turns to one side and then to another one. If we look at the slow motion of this video, we can see that from the torsional motion, some of the energy is transferred to sort of transitional motion and a wave is formed. So our slinkies we used can be seen on this picture, and here are all the parameters of our slinkies that were measured independently for each of them. So now, first of all, let's look at the beginning of the phenomenon, the formation of dance. So what happens and what drives the phenomenon is that the radius is being changed. So when we twist or untwist the slinky, we increase or decrease the radius. And after we release the free end of the slinky, there's no force holding it back, so it is like moved outwards, and therefore it moves further and propagates. And basically what this means is that the torsional energy is being transferred into sort of translational or transverse energy. And what can be seen here in the beginning of the phenomenon is a clear coupling between the torsional and transverse wave that is being formed. And we will also confirm this theoretically. So for the wave propagation, how the phenomenon looks after it starts, we can see on this video that there are the two types of motion, the transverse wave and the torsional wave, where the transverse wave we can track as the displacement of the circle to some direction away from the center of the slinky, and the torsional wave as the movement of the free end of the slinky. And what happens is that both these waves propagate. Torsional wave propagates, the propagation of torsional wave we can see looking at the free end of the slinky, and transverse wave as the displacement. And we can see that torsional wave gets before the transverse wave, and then they meet up again. So what this means is that the transverse wave is somehow slower than torsional wave, and this is also confirmed theoretically from this paper we have cited, and we will use this relationship that was derived in this paper further in our theoretical model. We have also confirmed it theoretically, where we tracked the angular frequency of the transverse wave and the torsional wave and compared it with this relationship, and it matched. So for the untwisting behavior, we can see that a wave is being formed. And basically what happens is that as the wave forms, we have like uniformly twisted the slinky over the height, such that these lines are uniformly spread. And we can see that the top of the slinky dances with sort of constant amplitude and is being displaced with constant velocity, whereas the bottom of the slinky stays unshifted. So what are the dance properties we can explore? Those are the amplitude of the transverse wave that we observed, the wavelength of this transverse wave, and also the property we call time of dance, or time until the lines on the slinky align to their original position when there's no torsional displacement, just like the wave-like phenomenon has spread over the whole slinky. So it's like 1/4 of torsional oscillation period. So we will be looking at these parameters and compare them theoretically and experimentally. So for the theoretical model, first look at somehow force approach and how we can model the spreading of the transverse wave. So we can sort of model the layers of the spring somehow discretely with rings connected by springs, because this system has really similar properties to Slinky. It has both transverse and torsional elasticities that are important in this phenomenon. So what happens is that there is some circular motion happening as one of the floors is displaced. So therefore, there has to be some centripetal force. This can be derived basically from the elastic forces that are acting on the Slinky, both the floor above and below the floor that we are looking at are acting on the floor with somehow elastic force, which acts as centripetal force in this phenomenon. And also we can define properties like the amplitude of transverse motion, which is the distance of the center of mass of the circle from the center of Slinky, and also distance between the centers and angle between them. So centripetal force is like a vector sum of these two elastic forces, and we can express both of them, and from that we obtain the relationship of angular frequency of the transverse motion based on the angle of displacement of two consecutive floors. And based on the geometry, we have a certain number of floors on one wavelength, and it is like obvious that the ratio of the number of floors in one wavelength to the number of the number of floors in the whole Slinky should be equal to this expression. And we can also tell that number of floors in one wavelength well, the angles should add up to a full circle. So from that, we can express also the number of floors in wavelength from the angle. And from that, we are able to obtain the omega, or the angular frequency of the torsional wave, and period of dancing, or time of dancing. And well, for the wavelength, we need to also like express how the angle between two consecutive floors looks. And from the ratio of the torsional and transverse angular frequency I have mentioned earlier from the paper, we can also obtain an expression for the wavelength of the transverse wave that is spreading through the Slinky. And now we are still missing the amplitude. So that can be calculated somehow from energetical approach. Until now we were looking at forces, now let's look at energies. So the energies we identified are present in this phenomenon as well: the torsional potential energy from twisting the top of Slinky, then torsional kinetic energy from like torsional movement that is being present, then transverse kinetic energy from this sort of circular movement when one floor or some floors of the Slinky are displaced and moving, and also the potential transverse energy, which is purely just from the displacement. And for now, let's assume energy is conserved. So in the time of release, there is no motion. We have just torsional potential energy, and all of the other energies are zero. In time of alignment, well, since the Slinky is aligned, there is no torsional potential energy. However, all other potential energies and motion kinetic energies are present. So from that, substituting into the equation, we can like express everything that is present in this equation and obtain final equation for amplitude of the motion, which depends on measured elasticities and radius of Slinky. Also, I said that we will prove that coupling is present, and it can be analytically derived because not like all torsional potential energy gets transferred to torsional kinetic energy. Some of it also goes to transverse energy, so that is the proof of coupling. And you may be asking if there are also some friction losses. Of course, there are. We can calculate them based on the distance that the Slinky basically travels, and we can incorporate them into the equation, energy equation, from which we calculate amplitudes. And we can see, like intuitively from this, or qualitatively from this graph, that the energy of, potential energy of twisting is dependent on number of turns to the power of 2, however, friction just to power of 1. So as we increase number of turns that we do to the Slinky, the frictional energy becomes less important, and it actually converges to the original amplitude. Now let's compare the experiments versus theory. So we have received a match for the time of dance, or time of alignment. When the Slinky is whole dancing, the wave-like phenomenon has spread. It is a great match. Also, for the wavelength, we have received a great match on number of turns versus wavelength in our experiments. And both on the amplitude, we can see both the line without losses and with losses, we receive a great match. We have also compared time of dance and wavelength and also amplitude for different types of Slinkies, and all of these experiments match our theory. So to conclude, we explain the phenomenon using coupling between torsional and transverse waves. Then we measured parameters of our Slinkies, derived theoretical model based on force and energetical approach from which we could characterize the motion, and then conducted the experiments and compared them to our theory, and they matched really well. Thank you.
Thank you. questions from the opponent.
All right. Thank you, reporter, for your very insightful report. Yes or no, please. Can we say the phenomenon is a projection of circular motion of rings onto a vertical plane?
Yes, I would say so.
Are the three types of motion, longitudinal, transverse, and rotational
No,
motion?
there is no longitudinal motion considered.
Okay, so are the two types, the transverse and
Yes.
rotational motion, independent of each other?
No, they are clearly coupled.
Okay, can you go to slide 27?
Sure. 27. Here. Okay.
Okay, is omega transverse the rate of change of phi? Or
No, it's the omega of the wave spreading.
Okay, thank
The
you.
transverse
Did you
motion.
assume that
Phi
phi
is
is a
constant.
constant?
Sorry?
Did you assume that phi is a constant?
Yes.
Okay, can you go to slide 39?
39.
Yes.
Okay.
At what time of motion is this equation valid for?
It is valid for combination of transverse and torsional wave.
Okay, thank you. Can you go to slide 51?
51.
Yes.
Mm-hmm.
What does the slinky height refer to? Is it the original height or the height
Yes,
during
the
the dancing?
original height.
The original height. Does the slinky's height change during the dancing?
Yes, it changes slightly.
Okay, thank you. Can you go to the slide where you talked about how you modeled friction?
Sure. Sorry, it's here.
So you account for some normal force gradient, right? How the lower rounds have
Yes.
higher normal force? All right, thank you. Can you go to, okay. How did you release the slinky experimentally? Was it by
We
hand?
released it by hand because there is like no sophisticated enough mechanism
thank
that
you.
could produce better results.
Did you assume that the slinky rings are always circular?
Yes.
Okay, thank you.
Thank you. Okay, could I ask for the attention of the audience? All right, please.
All right. Good morning, everyone. I'm Lucas from Singapore, and today I'll be opposing problem number 5, dancing slinky. Let's start with a summary of the report. The reporter qualitatively explained that dancing is a superposition of torsional and transversal waves, and it's also a projection of the circular motion of each rung onto a vertical plane. She quantitatively used forces and energies to obtain analytical expressions for wave properties, and she experimentally varied the slinky diameter, the number of flaws, and the initial twist. Now let's move on to some strengths of the report. Firstly, I believe that the report had a qualitative explanation for the dancing motion. I think it was great that she explained how the dancing motion actually results from circular motion of each individual rung. There was a quantitative model that leads to analytical expressions for wave properties. I think it's great that she used a simple theory that gives us analytic expressions, so we can directly see how every parameter affects the wave properties. She also accounted for the normal force gradient along slinky rungs in the friction modeling. And I think this is very important because you can imagine that the lower rungs of the slinky actually experience a higher normal force and friction because there are more rungs above it. Finally, she had a great experimental scope where I think she varied a large number of parameters such as the initial twist, the slinky parameters, and I think by varying so many parameters, it allows us to prove that the theory has great predictive power. Now for some areas for improvement of the report. Firstly, I think that the theoretical model does not predict dynamics or have any form of time dependency. I think that position time verification is very important in this phenomenon. As the problem statement states, the slinky may start to dance. And while I do commend the reporter on having a simple model, I think that these oversimplifications can result in their model not having any time dependency. And having time dependency will allow us to see many more interesting trends. Next, her theoretical model does not actually model the transient torsional potential energy. In her energy balance, she only has an initial torsional potential energy term. And I think that there's no potential energy term on the right-hand side to account for time dependency. From the videos in the report, we see that the slinky's lines are actually aligned diagonally during the dancing motion, meaning that there should still be some rotation of each rung relative to the previous one. This means that there will be some torsional potential energy term that is not accounted for. Next, I think that the expression for the period of the transverse wave was inaccurate because phi is actually time dependent, where phi, I assume, would be the relative angular displacement between two rungs. And we expect the angular frequency of this rotation to also be time dependent. So it's incorrect for her to just take some 2 pi over omega because her equation is actually not uniform circular motion or simple harmonic motion, and we can discuss this further in the discussion. I also think that her qualitative explanation was a little bit unclear when she brought up the toy model of the slinky that considers the two forms of motion independently, which I think is very unphysical because intuitively, when we twist the slinky, the height will change. We will experience a restoring force and torque, hence these spring constants cannot be considered independently. Mathematically, a length constraint forces the rotational motion to be a change in height. Hence, we cannot model them independently. A possible suggestion could be to consider the bending moment energy through the change in local curvature and a length constraint. This accurately models all three modes and reduces our problem from all two modes and reduces our problem from a two-dimensional problem to a one-dimensional one. Finally, I think there were a few poor experimental controls such as the hand release, and they could have used magnetic tape instead. I would like to invite the reporter up for a discussion now. Okay. First, let's clarify some of your spring constants. So, were these independently measured or were they fitted?
Yes, they were all independently measured. We measured both the transverse elasticity, and found out that it was linearly elastic, and both the torsional elasticity, and it was also linearly elastic.
Okay, so to confirm, you measured them separately.
Yes.
Do you think that
we measured the torsional elasticity by hanging a weight on one end of the spring,
I understand.
And the transverse elasticity by displacing.
Yes, I understand. But in your report, you have repeatedly mentioned that these two modes of motion, the transversal and this longitudinal, are coupled, right?
Not longitudinal.
Oh, sorry.
I think you,
Did I
you
did I
mean
misspeak?
the transverse and torsional.
Yes, sorry, the transverse and torsional. You mentioned
yes,
that coupled.
they are coupled. Their velocities are coupled, and also like qualitatively, we can explain that the origin of motion actually comes from the coupling.
Yes, I agree. So if they are coupled, I don't think that you should be able to measure their spring constants independently, right? Because their spring constants should actually depend on each other.
Actually, I think we can measure them independently. Of course, like there is some also like coupling, let's say, or some relationship between these constants. However, by these measurements, they can be measured independently.
Okay, I think I will probably disagree with you on that. So we can imagine that these constants don't actually have much physical significance since they are actually interdependent. I imagine that the only constant that actually affects the restoring force of the slinky would be the Young's modulus or bending moment or bending stiffness of the slinky, right? And these spring constants are really just some geometric relation to the bending stiffness. Will you agree with me?
I think like it is valid to measure these constants independently and put them in the theory, because like in these directions and the in which the constants are measured, I think like the force acting is somehow independent, so it can be measured independently. However, I agree that there is like some connection between these two.
Okay, yeah. So I'm glad that we agree that there's some connection between the two, and while I think that for purposes to simplify the theoretical model, it might make sense to measure them separately, but I still believe that they should have been calculated geometrically from the Young's modulus, for example. Now let's talk about your conservation of energy equation.
So we can look at the conservation of energy. Do you want me to go through it once again, or?
No, it's fine. So from what I see, there is no torsional potential energy term on the right-hand side.
There is torsional potential energy.
However, that's the initial, right?
That's the initial. But when we are modeling like the dance as a whole, that the whole slinky is sort of dancing, is when it's become untwisted. And like all the torsional potential energy has turned into the torsional kinetic, transverse kinetic, and transverse potential energy.
Oh, I see.
Like we can see on the phenomenon demonstration, for example, that the slinky untwists. Then when it's completely untwisted, the wave is spread along the whole slinky, and again twists, and the wave is only on the top.
So just to confirm, your fully untwisted would be when all the black marks line up, right?
Yes, exactly like that.
But when all the black marks line up, wouldn't the slinky just be some uniform cylinder? Why would there be an amplitude? What amplitude are you even solving for?
Because there is the coupling, there is the transition of energy between the transverse and torsional wave. So therefore, some of the energy over one period from the torsion wave goes into the transverse wave. It's not just a simple cylinder, because, well, the energy has to go somewhere, and it doesn't go like only into the torsional kinetic energy, as we can see, but like 2 to 4% go also to the transverse
I understand. So
wave.
do you have a picture or a video where it crosses this point?
Yes, sure.
And maybe we can verify if it's actually a cylinder.
I can show you here that it's not. Like when it passes through the center, it is this wave-like.
I really cannot see the point where it passes through the center. I'm sorry. Okay. I guess we will probably have to agree to disagree on this point then.
Like, why do you think it should be just cylinder? There would be like no coupling, no exchange of energy. Why should it be just cylinder when it is all aligned again?
Well, I was just raising the cylinder as a more extreme case, because you do not know that your amplitude is maximum when these all line up, right? It could be maximum at a different point.
It's something like this. Let's say that this is the wave-like boundary of the slinky, and the points will be sort of like this. So, but they are not turned; they are just displaced in this direction.
Yes.
So there is no like torsional energy, just this transverse energy
Yeah.
in
So
this direction.
how do you know that the amplitude of the wave here is maximum at this point in time?
It's not maximal at this point of time. Actually, it's the same throughout the whole
It's the same
motion.
throughout the whole motion.
However, what changes is
Oh, I
we
see.
can see
Okay.
on this slide. For example, here you can see it.
Okay, yeah,
quite
I'm
great.
sorry, but I think I'll have to cut you off here. Okay. Now let's talk about your expression for the period of the transversal wave,
Okay,
if
sure.
possible.
The period of.
So if I'm not wrong, you write some expression that looks like omega equal to what? Phi root k over m. And you mentioned that your phi is a constant.
Yes, can I explain?
Just to clarify, phi is the angular displacement between each rung, right?
Yes, phi is the angular
Okay, so
displacement,
how
like,
is phi a constant? I don't believe
if
that.
I have like the floors like this, so the phi is angle between each floor when the motion has started, when there's the transverse wave going on, and we can say that these floors are actually equidistant. Like the phi between each of these floors is is the same because it's sort of like circles on a spiral.
So I understand your diagram, but I don't really agree with your explanation at all. Because
well, this is not the omega
sorry.
for this phi, you know. This is the omega of the transverse wave.
Oh, it's a different
not
omega.
of like this oscillation or so. It's not like omega, the rate of change of this phi. It's different omega.
So omega is this omega.
Omega is like the angular frequency with which this wave is spreading.
And they are not the same.
What do you mean?
Are you sure the omega for the circular motion of each circle to not be the same?
Oh
as
yeah,
the
it
dancing?
should be.
Wait,
because
so
it's just like a projection.
So is this phi dot or not?
It's not phi dot because phi dot is like the
Okay, I
displacement
think
of two
I
consecutive
think
floors,
this discussion
and they are
is
all traveling like with the
going
same
nowhere.
velocity.
All right, I'll just say that I disagree that phi is not a constant, because if phi were a constant, you could imagine that the entire Slinky would just be rotating as like a rigid body, because every single rung is fixed to the next rung, and I don't think this is correct.
Well, in the case when
okay.
the wave has spread, it is correct, and in the other cases, the bottom is just standing and the wave is just on the top.
Thank you. So
I believe.
finally, let's talk about some of your experimental trends, if possible.
Okay.
You had some graphs where you plotted some wave properties against a parameter, right? Could you just run me through some of those?
So, for example, here we have the time of dance, which I explained is basically like 1/4 of the period of just the torsional oscillation. And since it's sort of like harmonic torsional oscillator, there's no reason why the period should change over the initial displacement.
Okay, so did you ever plot the amplitude?
Sorry?
Did you ever plot the amplitude of the dance on the y-axis?
Amplitude of the dot, of the wave.
While you're finding the slide, could I just ask how this amplitude was tracked? Did you just
Yes, it was tracked basically from
camera
snapshots from the video,
I see.
and we have identified like the maximal and minimal point of the transverse wave on the side of the Slinky, and that was basically 2 times the amplitude.
So your amplitude depends on the number of turns. Wait, I don't see a number of turns.
My amplitude is like, if we consider energy conservation, it is constant over number of turns. However,
so
when
even at 0 turns, there's still some amplitude?
Not actually, if we introduce friction, because friction is linearly dependent from number of turns.
I see. Okay.
Thank you.
I think it's great that we clarified that.
However,
Thank you both.
the energy is on.
Final remarks of the opponent.
All right, to summarize the discussion, I first started by clarifying some points on the reporter's quantitative theory. We talked about how the spring constants mentioned were all characterized separately. I believe that this is not physical, as the reporter herself has mentioned that the transverse and torsional motions of the Slinky are coupled. I suggested that the bending stiffness could have been characterized, as both spring constants are geometrically related to that. We next move on to the point that there was no time-dependent torsional potential energy component. I pointed out that if the Slinky was fully untwisted, which is the only time where the time-dependent torsional potential energy would be 0, the Slinky will have no amplitude, or we do not know if the amplitude is even maximum there. Next, we talked about her expression for the period of the transversal wave. I pointed out that phi, the angular displacement between each rung, is very much time-dependent and not constant, as her model assumes that if that were the case, the whole Slinky will rotate as a rigid body. Finally, we discussed some experimental trends. In conclusion, I believe that the reporter has not fully answered the problem statement due to a lack of investigation into time-dependent motion and oversimplified theoretical model. Thank you.
Questions from the reviewer?
Hello, I'm Jian Zhang from Team China, and there are some questions for the reporters. Why did you choose the discrete rings model instead of modeling the slinking as a continuous elastic spring?
Because modeling it as continuous elastic spring would not allow us to have analytical model.
Okay, I see. And the next question is you mentioned omega transverse to omega torsionals equals the square root of 2 divided by 2. And under what assumptions was this relationship derived, and has the equality of these two frequencies been verified in experiment?
We took it from this paper because it was really elaborate and did not want to include the whole paper.
Yeah, and do you verify this in experiment?
Yes, we have verified it.
Okay, and the next question is how large or the typical oscillation angles? And I see you use small angle approximations in force analysis.
I think the biggest angle that was used for the small angle approximation was up to 20 degrees. So
okay,
it's still
I see.
less than 2%.
Yeah, let's turn to the next questions. And how did you precisely measure the time of the dance and wavelengths from video? Did you use video tracking or?
Yes, we used video tracking and we measured the properties based on snapshots from videos.
Yeah, and the last question is: did you observe or measure any out-of-plane motion during the dance, or could it affect the transverse wave behavior?
What do you mean by out-of-plane motion?
Like just move around the.
Yes, that was classified as transverse motion, and like the twisting itself of the Slinky is torsional.
And there's some questions for the opponent. Do you think it is possible to measure slinking properties independently?
No, I do not think it's correct to do that. You should just measure the Young's modulus.
Do you mean that these properties can only be derived by parameter fitting?
No, I mean that it is not correct to separate these parameters at all because they both actually depend on the Young's modulus.
Okay, and the next question is how do you think phi will evolve in your opinion?
I mean, phi is definitely not constant because at the start, the phi must be 0. And then in the middle, you know that there's some non-zero phi. I'm not particularly sure on the actual function of it, but I know it's not constant.
Okay, and there are also some questions for the reporters. How many times were each experiment repeated? And what exactly do your error bars represent?
Each experiment was repeated 5 times, and the error bars are standard deviation.
Okay, and do you consider the systematically investigate how material properties like Young's modulus or shear modulus?
Well, we did not investigate that. However, we tried investigating also metallic slinkies. However, they were not sufficient for our experiments.
Okay, thank you.
Thank you.
Because of big losses.
Okay, could ask the reviewer to start.
Hello everyone, I'm Zhan Zhang from Team China, and I am the reviewer of the question 5, Dancing Slinky. First, a summary of the report. In the theoretical part, she considered two elastic properties of Slinky, the transverse elasticities and the torsional elasticities. And she also cognitively built the force balance models and the energy conservation models. And she also considered the Slinky as multiple interconnected rigid rings and approximated it using the small angle motions. And finally, she calculated the time of dance, amplitude, and the wavelengths, and compared it in the experiment part. And in the experiment part, she used different Slinkies and fixed it, used taps on the tables, and used hand to twist the springs. And he verified the time of dance, amplitude, and the wavelengths. The second part is the evaluations of the report. There are some merits. In the theoretical part, she combined the force balance and energy approach and used measurable parameters only, and there's no fitted values. She also modeled values types clearly. There are transverse and torsionals. And in the experiment part, she tested various linkages with different sizes, and there is a good match between the theory and experiment. But there are also some concerns. In the theoretical part, she criticized the range models may oversimplify real continuous linkages, and also she ignores the longitudinal elasticities and without justifications. There is also insufficient verifications for cited relationship, and there's wrong dimensions in amplitude loss analysis. And also in the theoretical part, there's no detailed error propagations or uncertainty analysis. And there is also lack of tests in extreme cases. And this page is about the evaluations of the opponents. And for the merits, they asked about the longitudinal motions and asked about the couplings between the transverse and torsional waves, and also questions time dependency of the theories and point out lack of experimental controls. And there's clear slide demonstrations and expression in discussions. And there are also some concerns. They did not point out the oversimplifications of the theories. It didn't ask about the control and the change of boundary conditions. Didn't questions about the extreme conditions, and did not ask about the influence of material properties, and failed to give enough useful suggestions. And this is where the discussions analysis about the topic of measurement of elasticities. Our own opinion is we agree with the opponent, and since there is a coupled relationship, the elastic modulus should be the super parameters to describe the deformations of the slinkies. And about the topic of conservation of energies, our own opinion is we agree with both, and the link between torsional energy and transverse energy is unclearly shown in the report, and just exists transverse waves when radiance is the same throughout. And about the topic of the phi, is it a constant? We disagree with the reporter, partially agree with the opponent, and due to energy dissipation, there should be a chance in phi. And there are some suggestions. For the reporters, she should clarify model eliminations and boundary conditions, and provide more details on experimentally repeatabilities, and add experimental investigation of initial condition. And for the discuss material properties more explicities, and for the opponents, they should focus more on experiment and didn't question the hand release method, and should introduce more suggestions. And thanks for listening.
Thank you. Final remarks of the reporter.
Okay, so in my concluding remarks, I would like to address a few things. So first of all is the release that was done by hand. So we believe only with hand you can account for stable enough twisting and release, because you can you have to twist the slinky and hold it, and it would require a really complicated release mechanism for the slinky not to be released by hand. So it was better in our case to do the release by by hand. Also, for the spring constants, I think it was valid measuring them independently. I agree with the opponent and reviewer that this can be done through some elasticity and Young modulus. It is a good suggestion. However, I think we obtained the same results as if we just input the Young modulus and calculated the Springs constant from that. Then there was a concern about cited relationship not being verified experimentally. So it was done, and we can see that the cited relationship actually works and fits our experiments. And then in the end, there was some concern about line alignment. So I want to say that when the line is aligned, the Slinky is not in the shape of cylinder, as we have seen in the video of the phenomenon demonstration, that it is actually not torsionally twisted, it is just like displaced to the sides. So I would like to thank both the opponent and the reviewer for a great discussion and great questions. Thank you.
Thank you. Could I ask both the opponent and the reviewer back on stage, and then we'll have time for jury questions? We start over here. Michael, can you start? And then Carrie?
I think.
Yeah.
Yeah? Okay. So my first question goes to the reviewer, please. You stated that there's wrong dimension in the amplitude loss analysis. Could you explain?
Excuse me?
You stated that you have wrong dimensions in the amplitude loss analysis you found in the report. What do you mean?
There was an additional dimension of a Newton for the last term, like the longest one. There's an additional dimension there that should not be needed.
Where?
On the second to last term, so that the RMG stuff. Yeah. Thank you.
N is, sorry, number of turns, not like normal force. It's or number of force, if you mean that.
I think we have to move on. Carrie, you had a question?
The dimension is correct.
Oh, yeah, my question was to the reporter. So I'm still not totally sure where you meant that you stopped analyzing the dents. You said when the points all line up. Was that at the very end? Sorry, was that the very end of the oscillating backwards and forwards, or just?
We are analyzing the dance after the 1/4 of period of like this torsional oscillations, when there is no torsional potential energy, like the lines have aligned and there is a wave along the Slinky. However, the wave can be observed also in cases when not like whole Slinky is untwisted and the properties remain the same.
So did the wave reflect up from the bottom? I mean, you see, or is that happening?
No, not really. Like, if we can look at the video, what happens in slow motion is basically that the wave spreads until the bottom, and then again, like from the bottom, it stops, and the wave is just on the top. So it doesn't like reflect on the bottom. However, it's more of a coupling
Next question.
Energy transfer mechanism.
Over here.
Yeah, so I have a question for the reporter. So in your model where you had this rings connected by springs, like this system, it could have extension and compression, but then your Slinky can't really like compress. Can you elaborate on how you implement this constraint in your theory?
Yes, well, this was just some sort of analogy that was used. Also, the Slinky can expand in this direction. However, this was not used in the phenomenon, and it was basically just for the assumption that there are rings connected and they are pulling at each other with some elastic energy force.
Yes, next question.
Could you go to slide number 15, please, with this equation from
Number
your
15?
literature? And you
Or
measured
15.
it?
15, 1-5.
Okay.
Yeah. With the equation, yeah. It's in the literature, you measured it, all good, but just very briefly, what is the basic physics behind this equation?
It is the coupling between the different modes.
Why is it around this amount?
I'm not sure exactly like why it's about this exact amount. However, the source of coupling is the free end, and that when it's turned, it also like displays outwards.
Short question, please.
Thank you. So shortly, what do we call dancing? Like when the wave propagates, or when it dances like this on the vertical, when the vertical axis moves?
Sorry, I'm not sure. What do you mean?
It is the dance when it
Oh,
reaches the
I
bottom
believe
vertically
that
or
dance
horizontal?
is like the wave we observe on the side, because well, the phenomenon problem
So it's a side wave.
statement says that it's a wave-like phenomenon from the side view.
Any further questions from the jury? Yes.
And I would like to ask the reviewer, they have just talked about this value taken from the literature. Do you think that this value is different on the different material of the string? So this value is from the literature, and you mentioned that it's important to also do some experiments with different strings, for example, metal one. So is this depending on the material of the string?
I can answer that one. Okay. So,
very briefly, please.
So I believe that this is not going to vary for the material of the string if the literature is correct and applicable in this situation.
Okay.
It should be a character for the shape and geometric
Thank you.
shape.
Thank you very much. Then I ask the jurors to proceed to grading. Is everyone done? Carrie, you done? You done? Daniel done? Viti done? Andreas done? Yeah, done. All right, we're ready. Could you show me the grades for the reporter, please? 5, 6, 6, 6, 6, 4, 6, 4, 6, and 6. Okay? All right, then the grades for the opponent, please. 8, 7, 7, 7, 7, 7, 7, 7, 7, and 9. Are we ready? Yes? Okay. Then the grade for the reviewer, please. 6, 8, 7, 8, 7, 7, 7, 6, 6, and 5. Thank you. Okay, let's start with the report. Let's start with one of the 6s. Tomek, may I ask you? Do we have a microphone? Yes, on my desk.
So I will start with my partial grades. So I gave you 4 for the report, and then 1.5 for the discussion, and I subtracted 0.25 for the discussion. And actually, you presented the solution for a very, let's say, limited setup, which although you presented that there were some other Slinkies you would like to show, all the presentation was done on the one Slinky. And then during the discussion, when the opponent brought some things concerning the lack of the model, you were not really aware that it's important to have also a real time-dependent model of the experiment, and you didn't not mention about the video measurements, for example, the frame rate and things related to the obtaining certain points for your graphs. I think that's
okay. Thank you. Itaya, can I ask you for the 4?
Yes. I have no problem with the comparison between the theory and experiment, but my major concern is the task fulfillment, because I believe there's a lot of time-dependent variables here. For example, it's clearly that the amplitude, for example, of wavelength varies with time. So when you say that you measure the amplitude for a particular number of turns, so it's not clear to me when you measure the amplitude or when you measure the wavelength, and that's the major concern for me.
Okay, and the partial grades?
Oh, thank you. 2 for the report and 1 for the discussion.
Okay. Thank you. For the opponent, I will start with Michael for the 9.
Yes, okay. So I very much liked your questions asked, so I gave you all points for that, because that were mostly the same questions I would have asked. The position speech was quite efficient and well done. You get 3 points for that. And in the discussion, you also pointed out that you understood what we were talking about, and lots of legs of the report were discussed, and I gave 3.25 and no subtraction, so I landed at 9.
Okay, thank you. Miai for one of the many 7s, but I just picked you. Sorry.
Questions, good. Questions asked, they were quite good, 1.5. Opposition speech, mostly relevant things, pretty good on the good side, 2.5. Discussion with the reporter was just for me rather than average, because many things could have been discussed way more detailed. For example, many experiments were somehow shown for milliseconds, and I would have wanted to see it a bit more detailed and talk about it a little bit more, and spend sometimes a bit too much time on things which were not in the presentation, but still very good.
Okay. For the review, we have 2 8s. Can I ask you? I believe you're one of the 2.
So I gave a 8 for the review. So I thought the major strength of the review is that you showed good understanding of both the report and the opposition. For example, you were really like engaging with it, pointing out the dimension and the small angle approximation and things like that. What you could have done a little bit better is I feel like towards the end, towards the discussion analysis, you were slightly rushed. So maybe spending some more time on that would have been nice, and maybe potentially pointing out some new like missed physics would have been nice. So my partial scores are the beginning 1.25 for questions, 2.5 for report, 1.5 for opposition, 1.25 for discussion analysis, 0.25 for missed point, and that adds to 7.75, and then I rounded to 8.
Okay. We also have a single 5 all the way on the other side. Michael?
Yeah, it's once again me. So the questions asked, I found some of them were already discussed in the discussion, and there I gave 1 point. And for the review of the report, I was quite satisfied with that, with 2 points. However, for the review of opposition and discussion analysis, I gave 0.75 for both. It was partly hard to understand and very rushy. And you couldn't convince me with my jury question, and I didn't understand at the end again what you meant, and therefore I subtracted 0.25 and ended at 5.
Okay. Thank you very much. That concludes stage 3. Thank you all for this interesting fight. If you all want to still have lunch, then please be back at 12:05 for the final stage. Thank you. And then we can start with 1 minute for the reporter.
Is it this? Test. Okay. Okay, I can start now. So, okay, good morning, everyone. I am Duan Yu, and today I will be presenting problem 9, magnetic assist. Here's the problem statement. We are to investigate the interesting motion of a magnet suspended above 1 or 2 base magnets. Here is an overview of my report. On to the introduction. A pendulum magnet was suspended with a string on top of a fixed magnet. A camera placed 2 meters away records the motion of the pendulum, while a 45-degree mirror allows tracking from a perpendicular direction simultaneously. Lastly, a projector is used for lighting. To model the motion of the magnet, we first write down the generalized coordinates of the magnet, the polar angle, theta t, and the azimuthal angle, phi t. To model the tilt of the magnet, we also have a polar and azimuthal angle for the pendulum, theta r and phi r. We then write down Newton's second law for the system, accounting for the gravitational force, magnetic force, as well as the dissipative and fictitious forces. The main source of dissipation is friction inside the string, so we modeled it as a dissipative force that is proportional to normal force. Now we also need to model the magnetic force between the 2 magnets. We model the magnets as current cylinders. The magnetic field created by the bottom magnet is obtained from the Biot-Savart law, and the magnetic force and torque acting on the pendulum are obtained by integration. Importantly, we must characterize the magnetization of the magnets. To do so, we use a Hall probe to measure the magnetic field along the axis of each magnet, fitting a curve to the following equation to obtain the value of magnetization. With the experiments and theory covered, let us now examine the single base magnet motion. In our investigation, we chose to focus on a centered base magnet placed right below the pendulum magnet at rest. The motion is set off with an initial tangential impulse. At first, the pendulum's motion appears uninteresting, just like a gravitational pendulum. There is a single central force. With some initial tangential velocity, we might expect to see a familiar elliptical motion pattern. However, plotting the theory and experiment for a pendulum, we can see that a flower trajectory is formed. To better visualize how this motion varies over time, let's plot the polar angle theta and the azimuthal angle, angular velocity phi dot. We notice an oscillatory pattern where the maxima in theta correspond to the minima in phi dot and vice versa. This type of motion is characteristic of conical pendulums, so let us understand it better. Initially, when theta is large, the pendulum magnet is further from the center and has a low angular velocity due to the conservation of angular momentum. The central forces will overcome the centrifugal forces, initiating a decrease in theta. Now, when theta is low, the magnet has a large angular velocity and strong centrifugal force directs the magnet outwards, increasing theta again. The cycle then repeats periodically. Having understood the fundamental motion, we may now dive into the most interesting part of the single magnet regime, the flowery patterns. There are two parameters we may use to characterize these orbits. We begin by discussing the eccentricity. Depending on initial release conditions, we see that some motion patterns are more circular, while others are more flowery. This motivates us to define an eccentricity eta as the difference between the maximum and minimum polar angle of the first oscillation. Upon releasing the pendulum with increasing angular velocity, we see that there is lower eccentricity observed. In other words, faster release speeds create more circular trajectories. To explain this, we notice that the initial angular velocity is large. The centrifugal force is large, which prevents the pendulum from coming closer to the center, maintaining a more circular trajectory. Now let's discuss how the orbit may precess over time. We compare the motion with and without the base magnets. Without the base magnets, the orbit has minimal precession, while with a magnet present, there is significant precession. This is due to Bertrand's theorem, which states that only harmonic and inverse square central forces can yield a closed orbit. Since the magnetic force is far from satisfying either of these conditions, the orbit is not closed, and we observe precession of the orbit. To quantify the precession, let us define the precession angle. We draw two lines from the center, passing through the first maximum and second maximum of the orbit. The angle between these two lines is the precession angle delta alpha. Once again, we increase the initial angular velocity and plot the precession angle. Unlike our eccentricity graph, we notice that there is an increase followed by a decrease. This suggests the possibility of having two competing effects. First, let us understand the meaning of this graph intuitively. Effectively, the greater the precession angle, the fewer petals there are in the flower. At low and high initial angular velocities, there are 8 petals. Yet, at moderate angular velocities, there are only 6 petals in the flower. Let us begin by considering the decreasing trend in the latter half of the graph. We recall that there is minimal precession under just gravity. With larger initial angular velocities, the pendulum magnet is further away from the base magnet, and gravity dominates. Thus, the precession is less present. However, we still cannot explain the opposing trend at the left end of the graph. In fact, when we plot our theory without accounting for the tilt angle of the magnet, the precession angle simply continues to rise. This suggests that the pendulum's tilt is critical at low angular velocities. When the initial angular velocity is very low, the centrifugal force is also very low. This allows the magnet to get close to the base magnet, where a significant magnetic torque will rotate the pendulum magnet towards the base magnet. In this rotated position, the horizontal magnetic force is much smaller, leading to a lower precession torque and angle. Having fully accounted for this intriguing trend, we can conclude our single base magnet study. Now, onto the double base magnet case. We place 2 base magnets symmetrically as shown and impart a tangential impulse to start the motion. Plotting the azimuthal angle phi against time, we observe that first, the pendulum moves in a quasi-periodic regime. As it loses energy, it enters a chaotic regime, and is eventually trapped at one of the base magnets. Let us begin with a quasi-periodic regime. On first glance, the motion is similar to the single magnet motion. To confirm this, let's take a closer look at the motion time graphs. Once again, we plot the polar angle theta and the azimuthal angular velocity phi dot against time. At first glance, we see a striking resemblance to the one magnet motion. However, we cannot explain these oscillatory fluctuations in amplitude, otherwise known as beats. Why do beats occur? Let us plot the potential energies of the magnet system, with the equipotential lines highlighted. Given some total energy of the magnet, it has to stay within a region bounded by one of these equipotential lines. However, we notice that this shape is wider through the horizontal and narrower through the vertical. Plotting the slices of the potential energy in the horizontal and vertical directions, we realize why oscillations in the horizontal mode have larger amplitude and vice versa. We recall that our magnet will exhibit elliptical motion that precesses over time. When we begin the motion, the ellipse is elongated, so theta has a large amplitude. As it precesses towards the vertical direction, the steeper potentials will constrain the motion, narrowing the ellipse. In that case, theta will have lower amplitude. In other words, the asymmetry in the potential well is the key reason for beating. To further demonstrate this, let us now increase the distance between the magnets, further increasing asymmetry in the system. We observe that the beating amplitudes indeed become larger, verifying our explanation that greater asymmetry intensifies beating. After the quasi-periodic regime, as the magnet loses more energy, its motion becomes chaotic. In a chaotic regime, we see unpredictable motion paths which appear random. To explain this, let's go back to our potential energy plot. Zooming in, we can see the presence of a saddle point, which holds both stable and unstable trajectories in different directions. Close to this saddle point, the trajectory the magnet takes will be extremely sensitive to the current state of the pendulum, making it chaotic. However, to truly verify the chaos, we need a quantitative measure, the Lyapunov exponent. To compute the Lyapunov exponent theoretically, we add a small perturbation, delta naught, to the system and track the deviation delta. This deviation follows an exponential trend. The exponent lambda characterizes the rate of divergence of nearby trajectories, and a positive value indicates a chaotic system, which is what we theoretically obtained. Experimentally, we can also estimate the Lyapunov exponent by tracking how neighboring trajectories evolve in a massive experimental data set. By taking the logarithm of the deviation, we obtain an estimate for the Lyapunov exponent, which is close to our theoretical predictions. Hence, we have shown that saddle points cause chaos. We may confirm this by decreasing the distance between the base magnets. Plotting the new potential energy graph, we see the unstable direction of the saddle has become much gentler, causing less chaos in this system. This agrees with both our theory and experiment in the smaller Lyapunov exponent values. After further damping during the chaotic motion, the magnets will eventually settle towards one of the base magnets. Let's look at the basing of attraction. Green regions correspond to magnets coming to rest at the green magnet, while red regions correspond to the red magnet. The fractal basing boundaries indicates chaos for almost all initial conditions except for pendulums released close to the base magnets, which have low energy and bypass a chaotic regime. Looking at experimental verification, we can see a good agreement. The black points indicates chaos, and we can verify that the low energy region indeed is non-chaotic. We have now accounted for all three regimes, and we can conclude our study on the two base magnet motion. In summary, I quantitatively modeled the motion of the magnet with current cylinders, investigated one base magnet, and characterized the orbits of the pendulum. Investigated the different regimes with two base magnets, with quasi-periodic regime, chaotic regime, and the basing of attraction of the system. Thank you.
Thank you. Questions from the opponent?
Okay, thank you. First, I would like to ask if you included gravitational torque in your calculation.
I believe so, yes.
Okay. And the next one is, how do you measure air resistance coefficient or friction coefficient? Because you apply it in your theory.
Oh, we use one-month experiment and fit it to that and use the same value for the rest of the graphs in this report.
Okay, thank you. And also, is there a relation between eccentricity and precision angle in the 1 magnet case?
Well, I believe there are different things we can characterize the orbit with.
Okay, maybe we can discuss about that later. And in your precision angle measuring, is delta alpha measured one time or multiple times?
So could you repeat?
In the precision angle measuring, did you measure delta alpha one time or multiple times?
We measured it one time.
One time, okay. And how exactly did you verify your attraction basin? Can you explain that?
So we release the pendulum at these positions and we release it like plus 5 times to 10 times. And if it always lands on the same spot, then it is not chaotic. But if it always lands on, like, let's say it lands on one spot 5 times, that time, that spot 5 times, then it's chaotic.
Okay, I know what you mean. Thank you. And is parallax considered in experiments?
No, because we place a camera far away, 2 meters.
So you place a camera under or up or
it's
above,
sideways.
or
So if the pendulum is
sideways.
yeah.
Okay, thank you. And what is your release mechanism? How do you release?
We release it by hand.
By hand.
Yes.
Okay, thank you. And what is the connection mechanism between the string and the pendulum?
We have a hook on the pendulum and we tie a string to the hook.
Okay, thank you. And do you quantify the size of the basin, attraction basin?
Sir, could you
sorry,
elaborate?
time is up.
Sorry,
Thank you.
I don't understand. Sorry.
Then you have time to prepare. Okay, please start.
Okay, hello everyone. I'm Wei Ranyu from Team China, and I'll be the opponent of problem number 9, magnetic assist. First, the reporter provide a quantitative model to explain the motion and design and conduct reproducible experiments. Their experiment and theory reach quantitative agreement. However, I don't think that's enough. And the qualitative explanation are also not enough, especially for the attraction basin. And for the theory, first they analyze the magnetic interaction and calculate the trajectory of the pendulum. They also analyze the influence of different parameters, such as the parameters in the one magnet case and also the spacing between the two magnets in the two magnet case, and also analyze the chaotic phenomenon. For their experimental setup, they use a pendulum, use magnets, and they use a camera to capture the trajectory. And also for the verification, they verify the trajectory in their theory and also verify the attraction basin in their theory. For their theory, I think they considered all kinds of parameters in their theory. For example, the magnitude of magnet momentum and moment, and also string length, and also air resistance coefficient, and also calculate the trajectory and traction basin in their theory. And however, they lack some qualitative explanation. For example, the explanation on why the traction basin looks like that, and also the effect of tilting are just explained in small angle cases, and not explained enough for general situations. And also the size of the traction basin is not quantified, and I really have some questions about the applicability of Lyapunov exponent, and also they mentioned fractal patterns, but I don't see the dimension of fractal patterns. And also I have some questions about the gravitational torque. And for their experiments, they use a camera to capture the trajectory and control some of the influencing factors. And they compare their experiments with theory of the trajectory and also the chaotic phenomenon and also the end state, and that is the attraction basin. And however, I think they lack some detailed concerns. For example, the connection way and the release method, and also the verification of the fact that parallax can be neglected. And also, I think delta alpha is measured only once in their experiments, and I don't think that's enough. And also, the experimental data are not enough in attraction basin verification. They said they did like 5 times or 10 times for each point, and I don't think that's enough. And for the suggestions, I suggest they can quantify the size of the attraction basin and see how the size of the attraction basin changes when other parameters changes. And also they can use some statistical methods such as entropy to quantify how ordered exactly the attraction basins are. And also they can have some qualitative explanation of attraction basins and also improve the release method in their experiments. Thank you. And I would like to invite the reporter on stage. First, I would like to ask something about the size of the attraction basin, because the question part, I don't have enough time to ask you about that. Do you quantify the size of that, or like using statistical method to quantify how ordered it is or how chaotic it is?
Well, we use the Lyapunov exponent to characterize how ordered or how chaos it is. So the Lyapunov exponent will tell you the rate of divergence of trajectories, which give you basically how chaotic it is, right? So with higher.
I mean, the size of the attraction basin, like in which area the chaotic motion, the chaotic phenomenon is there, and in which region of area, or how big is the area where chaotic motion does not appear?
Oh, well, I think you just see from our basing of attraction plot. So, I mean, well, I mean, the part where I highlighted in the box looks quite,
okay.
Right? And the rest looks very chaotic. Because
yes, of course. However, you can see there's also some large area of like red and greens, but in your attraction basing verification, I see your verification for these areas are chaotic motion, right?
No, yeah, but okay, I guess well, you think that they're very like large, like I think you're talking about these kind of things, right? So
Yeah.
I think even though it might appear as large regions of stability, I think this is actually quite a small area. So maybe like 5-6 cms or around that. So I don't think that this region is actually quite large. Actually, even the region here is actually quite small. So I think it is okay to say that these regions are still chaotic.
So by saying small and large, I would like you to have some quantitative calculation about that. For example, you can introduce something like entropy, or just calculating the points where for the points where the area beside this is also red or also green, and for that you can calculate like the size of the attraction basin.
Well, I think the entropy will be not necessary because the Lyapunov exponent is quite similar to the entropy already. It's just a different value, but used in different contexts. But I believe both of them are invariants in the chaotic system, so that means that they characterize a chaotic system. I believe the Lyapunov exponent does it in a more intuitive way, so that's why I didn't plot the entropy.
I would like to disagree, because what I mean is that you can calculate the size of the attraction basin and see how it changes while other parameters changes, and so therefore you can see how the whole space is ordered or chaotic in different conditions with different other parameters, and I would like to suggest you to do that in further investigation.
Well, I think that definitely could be interesting, but yeah, I believe this is still sufficient for the limited time we have to present our work.
Oh, okay, thank you. And for the method to verify the attraction basin, can you turn to that page? Yes, and for the black dots, I believe you measured it for 5 or 10 times and see if all the if for all the times it goes to the red spot. Am I correct?
Yes, correct.
So will there be for the black dots is a probability of going to the red region exactly 50%, or there will be 80% or 60% or something?
No, well, the probability will be, of course, only 50% will be well, it depends on which point it is, I guess.
Yes. So you did observe 60% or 20%.
Yes.
Or
yes.
Yes. And so I would like to suggest that you can actually calculate theoretically the probability. For example, you can choose a point, and you can choose 100 points around it, and you can calculate in these 100 points how many of them are red and how many of them are green, and then you can calculate the probability and compare it to your experiments. And you can you can do more experiments. For example, for each dot you can do more than 10 times or 20 times or something, and you can verify the probability in your theory. And I think that's I think that can verify a lot more in your theory.
Well, I guess that could be interesting, but well, I do think that taking this data does take a lot of time, because there's many points you have to release it many times. So I'm not well, we can do it for the future maybe, but I think it might be very difficult to very time-consuming experimentally.
Okay, thank you. And I would like to ask if you consider initial velocity in in the two magnets case.
You mean the chaotic regime?
Yes, of course. Is the pendulum released from rest, or it has an initial velocity?
It's released at rest.
So how exactly did you release it?
We have a cutting board with us. So we have a cutting board which we can use to align the pendulum and release it at rest with your hand.
So how do you ensure it has no initial velocity if you release it by hand?
Well, you have to do it very carefully.
Okay. I would like to suggest to improve your release method. You can have for example, you can have something, have a clip or something to hold it at first, or some other method. And also, do you investigate how the initial velocity, how will the initial velocity influence on the chaotic motion, or for each point here, if the initial velocity changes, will it be in the attraction basin or outside the attraction basin?
Okay, wait. I have two responses. So first, about the release mechanism, we did try it using a gantry, but we realized that when the pendulum drops from the gantry, it has an initial velocity which is not controlled, so it hence actually works better. And for a second question, we did investigate having initial velocity, and I believe what will happen is it will go through first a quasi-periodic regime, and then it will go to a chaotic regime, and lastly be at the rest position. So that's what happens when you have a initial velocity.
So you mean like if even if you have an initial velocity, the results will be the same, or?
Well, I mean mostly I guess. I'm not sure what you're asking.
I mean like if you change the initial velocity, like when the initial velocity is large or something, will the attraction basin be different?
You mean the basin of attraction or the potential well?
The basin of attraction.
Oh, well, in that case, I believe it will be different because suppose you have a magnet release here at very high release velocity, then it will be the same as releasing from, let's say, a high position here with no release velocity, or like, when it reaches the highest point. So it will definitely look different.
So I would like to suggest to like further investigate something like that, because I think that would be interesting. For example, like at the green region, if you have initial velocity that is really high, it can have a chaotic motion.
Well,
right?
no, I think if you have, let's say, right here, like if you're pinching right here, like the base magnet is over here, and you release it with a high initial velocity, it will just go up, and it will be at rest when on the highest point. So at this point, so releasing it here with the initial velocity is the same as releasing it here at no initial release velocity.
However,
so I
sometimes
think it should be the same.
Sometimes it will have a tangential speed when like it reaches the maximum.
Oh yes, well yeah. So when there's a tangential speed, I believe it's actually quite hard to control the tangential speed. So you can't like release it at the same speed every time. So I think this might not be very feasible.
And also, I ask you about the gravitational torque.
Yes.
Yes. Because it will affect the direction of the magnets.
What do you mean by gravitational torque? Could you elaborate?
Yes, because the string, I can draw it like the string is on the top of the magnets, right? It's hanging.
Yes.
Right there. So like the gravity acts on this point, like the center of the magnets.
Yes.
So there will be a gravitational torque, because this point and this point, they are not in the same vertical axis, and because of the gravitational torque, like the magnets will tend to be like at this direction because of the gravitational torque. Do you consider that while considering tilting of the magnets?
Well, okay, there's no explicit term for the gravitational torque because we took torque about this point over here. But this motion you're describing is indeed accounted for in our equation for the center of mass of the magnet, which does have this angle. So it is accounted for in our model.
If you take the origin point as this point, then the force from the string will have a torque as well.
No, but we don't consider that because we use a set of minimalized generalized coordinates. So we didn't use the XYZ coordinates, we used the theta and phi coordinates. So in that case, we don't have to account for tension along the string because it is already implicitly accounted for in the center of mass of the pendulum. So it's like kind of using like a Lagrangian in that sense.
Oh, okay.
Yeah.
I think I would like to disagree about that. I really think the gravitational force or the drag force from the string will have influence on the direction of the magnet.
Well, we did account for it in our center of mass equation, so it is accounted for.
Okay, and do you consider tilting in all of your investigation, or just with the angle here is small?
Well, it's included in everything except for some of the chaos work because it will be more computationally efficient to use a model without tilting.
Thank you.
Thank you.
Summary of the opponent.
Okay, to summarize, first we discussed about the attraction basin, and I would like to say that if the reporter can further investigate like how to quantify the size of the attraction basin or like to quantify the entropy of this pattern, it will be better. And for the method to verify the attraction basin, I would like to suggest the reporter to verify like the probability of going to the red region. And therefore, it will be more valid verification for this theory. And also, we discussed about the way to release the pendulum and As the reporter has said, the release method that is using his hand to release is a good way because you can always release it carefully with your hand, and other method could have other problems, and I will agree with that. And we also discussed about initial velocity, and I would like the reporter to further investigate on that. And for the tilting, I would like to say that gravitational effect will have.
Thank you. Questions from the reviewer.
Yeah. Hello. So first of all, have you calculated the fractal dimension of your fractal basins?
Yes, I can show it later.
Okay, thank you. How do you verify your initial? So on slide 53, you have your
So
map.
slide 53?
53, yeah, the next slide. You have your various starting positions. So could you just reiterate, how many times did you repeat the same conditions?
Around 7, so 5 to 10 times. If it's
Did you release it by hand?
Yes.
Okay, thank you. To the point, do you think this is sufficient?
You mean 5 to 10 times?
Releasing it by hand.
Releasing by hand, I don't think so. But as he said,
Okay,
this is the best he can find.
To the opponent, is this system transiently chaotic?
Sorry?
Do we have transient chaos in the system?
Transient, I would say yes.
Okay, to the reporter, do you agree?
Due to damping, yes.
Okay, thank you. Do you think the analysis of the Lyapunov exponent done by the reporter is sufficient for this system?
For the system?
Yes.
I would like to say no, because Lyapunov exponent cannot tell us everything about this system, like the size of the traction basin.
Okay, thank you.
Yeah.
How have you modeled the tilting of the magnet? Because I was unsure from the discussion you just had.
Well, we introduced 2 more degrees of freedom for the tilt angle of the magnet.
Yes. So do you model it? Yes or no?
Sorry?
Do you model the tilt of the magnet?
Yeah, we have the 2 degrees of freedom for the tilt.
Okay, thank you. Further on, have you investigated an asymmetrical magnet arrangement in your system?
We have done some theoretical work on it, but we didn't do experiments.
No experiments, okay. Moving on, have you varied the string length of your pendulum?
No.
No. Which parts of your setup are made of metal, or do you have any parts of the setup which are made of metal?
Yeah, everything's made of aluminium.
So is the base metal?
No, the base is acrylic.
Okay, thank you. You mentioned you had an initial tangential impulse as well in the beginning for the single magnet case. You also released this by hand, correct?
Yes.
Okay, thank you. Did you assume that the suspension of the magnet was in the center, so the suspended magnet was attached from the center point?
Do you mean did I align the pendulum and the base?
Yes, so
we did.
Was the pendulum magnet suspended from the center? Do you assume this?
Yes.
Do you also verify this?
Yes, we used a laser to verify that it is vertical.
Okay, thank you. To the opponent, do you think this is sufficient analysis of this?
One magnet case?
Yes.
Yes, I think so.
Okay, thank you. Have you verified the Lyapunov exponent for various starting positions?
No, we have not.
Okay, thank you.
Thank you. Then you have time to prepare. Okay.
Hello everyone, I'm Alan from Team Germany. I'll be reviewing this physics fight on problem number 9, magnetic assist. First of all, going over the reporter side. We believe he had a sufficient system accounting, for example, for parallax error, and also modeled the magnets via Beer-Savallo, which is exactly what we would have done. Also, the eccentricity of the motion for the single magnet pendulum case was used as a quantitative analysis to analyze the motion. And also there was a precise description of the chaotic saddle node in the report. Sorry. However, there was an unclear usage of the metallic materials in the setup. For example, there was possible eddy currents which can form in the bottom magnets. And also, we were only able to clear up that the base was in fact non-conductive in my clarifying questions, which is crucial as the task states this. Also, the magnet is released by hand, so it's unclear how the initial velocity is controlled, as this was mentioned by the reporter. Also, there is no proof of the applicability of the dissipative function, as there are, for example, deviations in the theta prediction, for example, on slide number 17 for the Flary motion. We believe there is also a missing parameter variation, for example, the initial velocity, the string length, and also the change of the magnet's position, as well as, I think, strength as well, which are also crucial for a full investigation of the various aspects of this task. Finally, also most importantly, there is a missing multiple Lyapunov exponent variation. There was only one of them given, and for example, in the basins of the fractal attraction basins themselves, the exponent would be negative, which would prove that this area is in fact more controllable and not chaotic. Over the opponent, there were some relevant clarifying questions, and he does, for example, raise relevant topics like the release mechanism and the low quantity of data. There is also, however, a significant focus on the fractal basins, and he misses the different Lyapunov exponent dependency, for example. Over to the key questions, the opponent asked in the first question the characterization of the size of the stable state region. The reporter said that they used the Lyapunov exponent to quantify the chaos. And this was visible in the plots. In our opinion, this could have been investigated depending on various parameters, as we've just mentioned, for a full analysis of the entire task. However, we also believe that the Lyapunov exponent is sufficient to quantify the chaos, as entropy and Lyapunov are in fact physically related. Moving on to the verification of the fractal basins, the opponent questions the experimental methodology, and the reporter mentions they measure over different trials. We partially agree with the opponent here that the probability would be interesting to calculate theoretically, but difficult to predict. And the main reason for the comparison necessity would be the measurement in the comparison of the stable regions and the unstable regions, respectively. Moving on to the initial velocity in the two-magnet case, the opponent asks for the controllability. The reporter has said that this has to be released carefully. We agree with the opponent that the release mechanism should have been, in fact, improved, also for the one-magnet case for a high controllability, as releasing this by hand, in our opinion, is too sensitive, especially since we have a chaotic system. We also believe that the fractal basins would be affected through the initial kinetic energy released. Finally, the opponent asks if the gravitational force is accounted for. The reporter states that this is accounted for implicitly. In our opinion, we agree with the reporter, the torque modeling is not necessary if Lagrangian is used, and the model was sufficient. Now, however, we missed, for example, the parts of the side of the stable regions, whereas we only saw positive Lyapunov exponents. We missed the parameter variation and a quantitative investigation of different phases. So overall, we believe the reporter mostly fulfilled the task, had a good qualitative account, and the opponent partially fulfilled, for example, with an inappropriate Lyapunov calculation analysis missed. Thank you very much.
Thank you. Final remarks of the reporter.
Okay. Okay, anyway, so first let's start with the concern raised by the opponent. So first the opponent talked about the Lyapunov exponent, and I believe that, it is very applicable and it quantifies chaos. And I believe the entropy calculation proposed by the opponent does the same thing. Next, regarding the fractal basing of the system, we did investigate it, and I will show it in the next slide. Next, the opponent mentioned that we can investigate the probability of the pendulum ending up at the different magnets. And I believe that it could be interesting, but I believe it might not be necessary for verification purposes, and it might not be very physically insightful. And also, it's also very, very time-assuming to take the data for this. And next, for the release mechanism, we did try using a gantry system, but we realized that it was not very feasible. And so next, we have position time verification for the two-base magnet and initial velocity. And we said that the system will pass through the chaotic regime, and the position time verification is not possible. Lastly, for the gravitational torque, we accounted for it in our theoretical model. So here's the gantry release mechanism. We found it was worse than the hand release, and the fractal dimension is not an integer, which indicates chaos. So for the reviewer talked about the tilt of the magnet, which we accounted for theoretically. For the Lyapunov exponent, we investigated theoretically, but did not show not shown due to time constraints. For the initial conditions, we tracked it with a camera, and for the setup, we use all non-magnetic materials. And lastly, for the eddy currents, we believe it is insignificant. So here's the tilt-angle verification, and here's a Lyapunov exponent. So as you can see, the center is 0. So to summarize my report, I modeled the motion quantitatively with current cylinders, investigated the motion with one base magnet, and the different regimes in two base magnets. Thank you.
Thank you. Could all three go back on stage, and then we have time for some jury questions, and Georgi was fastest.
Thank you. In your experiment to the reporter, when the bob, like the magnet at the end of the pendulum, is not rigidly fixed, and the magnet also moves around, so the field changes, and when it is not rigidly fixed, the vector of magnetic moment changes. And my question is, in your theory, do you consider like that it changes instantly when it moves, the magnetic moment, or how do you model that?
We do not assume the magnet tilts instantly, so we will solve for the tilting motion of the magnet in our theory. Like we will solve for the tilting angle as it moves in a magnetic field.
Further questions? Michael?
Yeah, for the experiments with one magnet attached to the ground, for this flowery patterns, you need an initial velocity, it's right, yeah?
Yes.
Yeah, how did you get a reproducible initial velocity for your comparison with the theory then?
For our theory experiment comparison, we just use one run, so we will check the initial velocity with by just releasing it.
Okay, just per chance and track, and then you get a comparison. Okay.
Yes,
okay.
yes.
Andreas?
So, in the limit of the magnets on the table being very far away from each other, I just have a regular pendulum, right?
Yes.
Yeah. And if they are on top of each other, I meant in a single magnet regime.
Yes.
Yes. So how did you choose the distance between them to observe the chaotic motion? And if I want to do this, how does it depend on this distance?
Okay, so we chose a distance. So if it's too far away, then if we release it, it might not see the potential well. As in, if you release it, then it might not see the potential well when it goes to the center. So we chose a closer distance, so around the separation is around, I believe, 10 cm and 6 cm. And we didn't choose it to be too close, or else it would be too similar to the one magnet case.
Okay, Mihai?
Can we just take a look on your side where you compare the measured and the theoretical magnetic field values?
Okay. So for the characterization, is it this one?
I don't know yet, because I don't see the slide.
Oh, wait.
Careful.
Please, sorry, give me a second. Oh, all right, it's here now.
Then how big was your magnet actually? How high, and how was the diameter of it?
I think the diameter was around 1 cm, and the width is about 0.5 cm.
Okay. Yeah.
So in one of the appendix slides, you showed how you were able to actually like measure the magnet tilt. Could you please clarify in your camera setup, how do you do that exactly?
Okay, so for our pendulum, it is, maybe I take it out. So you can track like so we binarize the image and we track for the blue region here. So we'll fit a square to this region, and we can get the angle of tilt. So for example, if it's tilted like this, the rectangle will look like this, and we can get the angle from like this edge that you see.
Any further questions?
If you can go to the page 28 and just briefly explain why the theoretical curve isn't so smooth.
Oh, I think that's interpolation error because we did not run enough theory points for this because it was time consuming. So we just ran it close to the data points.
Is there any of the jurors who haven't asked a question who still wish to do so? Daniel.
Very short again, can you elaborate on how friction was considered? What was your dissipation function?
We used mu n, so that accounts for the friction between the string and the pivot, as well as some internal time in the string.
Okay, thank you very much. And then I'll ask the jurors to proceed with grading.
That's not fair.
We expect a little more and better.
Actually, I've got some points to discuss concerning how to choose jurors.
For sure, I like their qualitative. That part is great.
If everything's a simple as range, to other the same
it is.
And this has to be somehow regulated and taken into account of
More variation in the experiment, right? Changing the length of screen or changing the position of magnets. I think that makes this problem more interesting than as it is. Everything is pretty much
I can sit and say, okay, this room. No, but we have the record. You can say that this is the average of for the reviewer. This is the average. No, it's a single. It's a single. Let's say triple of characteristics for each juror. No matter. Okay, I choose that one, and to have the same to that one. Actually, because I'm not. But I will. In a personal discussion with whom? Yeah. I will.
Okay, I think we're all done. All right, for the final time this year, can I ask you to show me the grades? We start with the reporter, please. 7, 8, 7, 6, 8, 6, 9, 6, 9, and 7. Okay, and then the grade for the opponent, please. 6, 7, 8, 6, 8, 7, 8, 8, 7, and 7. Good, all right, perfect. And finally, the grade for the reviewer. 6, 7, 9, 8, 8, 7, 8, 7, 9, 7. Okay, for the report, Daniel, can you start?
Yes. I start with the partial grades. So I gave you 6 for the report, and I gave you another 1.5 for the discussion. So if you add these up, I had the option to round up or round down, and I decided to round up. The idea is that I really appreciate how you presented everything. It was very sensible. It was very clear to me. But I also saw that there could have been done a little more. Always when there are like questions that were a little bit critical, then you had to mention, okay, it's time consuming. I could have done more, but I think you were right on the way. So yeah, and I was consistent. So I gave it a 9. It's rounded up.
Okay. Vitaya, can I ask you for the 6?
Yes, I think your presentation is very well done on the animation, and the visualization is very clear. But to me, I have concern with the theory. You stated all the forces, like a frictional and also fictitious forces. I didn't have time to ask about those, and then that's it. I didn't see the equation of motion, like how they. I don't even know if you approach this problem from the Newton's law of motion or the Lagrangian method, because I didn't see that clearly. So that's my major concern. But very well done on the animation and all the visualization.
Okay.
So my partial scores are 3.5 for the report and 2 for the discussion.
Okay. Thank you. For the opposition, we have several 8s. Tomek, can I just pick you?
Sure, although I would like to talk about the reviewer, but okay. Let's start with the partial grade. So I have 125 for questions, 275 for the opposition speech, and 2.5 for the discussion with the reviewer. In my opinion, some interesting points were brought to the stage. For example, this entropy business, and also the discussion on the Lyapunov fractals were also very relevant to the problem. And they also ask about some experimental setups descriptions. All that was worth it, in my opinion.
Okay. Claire, you had a 6. Can I ask you?
For the upload, right?
Yes.
Yeah. I think that the reporter shows very straightforward, simple analysis of these problems, and there's much more variation experimentally they can work on it, and the opponent should have pointed out that instead of keep mentioning the like a minor thing or something that not relate to this particular problem, like entropy or something, you know. So you probably get a better score if you get into experimental part more. Okay.
And the partial grade as well?
Oh, my partial grade is like a 0.5 to 1 to question, and 2 for the report, speech, and 2 for the discussion is sum up like a round of 6.
Okay. Can I just stay with you then, just for the reviewer as well?
Okay. Well, pretty much same for the reviewer. I mean, reviewer had like a kind of average review for the overall, reports. So, I mean, it's not bad, but it's not good either. So, and I give a little bit more point on the discussion analysis. So it ends up like 1 on every session and 1.5 on the discussion analysis, and it round up 6.
Okay. We also had 2 9s. Carrie, could I ask you for a comment on the 9?
Yeah, sure. I gave a 9 the first round for the levitating fluid, so I'm basing myself on that a little bit. But yeah, thought it was good questions asked, 1.8, good review of the report, 2.5, and the reviewing the opposition, 1.5. But I particularly liked they were bringing out more points. There were missed points which were raised about the experimental details and things. So I added on another 0.5 for that, which meant it rounded up to 9.
All right. Well, thank you very much. I would like to also thank all jurors for their hard work this morning, and of course all 4 teams for a very interesting fight.